Hey, good afternoon and good morning. Welcome to this second day of the Cybersecurity for Robotics conference, broadcasting live from Leuven in Belgium and from other places in the world, Austria, Boston, and many others around. So, as the second day of this conference, we definitely welcome also our participants from out of the US. It's early morning over there, so welcome to all of you, and thanks for dialing in and for joining in. Yesterday we had an interesting first afternoon, talking about many different things, and none the least things which included an oversight and an overview of everything which is related to the industrial developments of robotics, and specifically also on some of the research activities that are happening. As you can see today, we are a little bit more in the time of the season, which is just the day before the Christmas period starts to hit here, and I'd say we've tried in any case to be a little bit more in the sphere. So I have my Christmas sweater on with the red rose reindeer and the Christmas tree behind me, just to make sure that everything works in that order fine. And maybe we'll switch a little bit later on with putting on some hats to at least get a little bit in the festivity mood later on. Well, today we're going to have an interesting afternoon session as well, talking about securing some of the robot systems, talking about embedded security, about how to secure basically the ROS environment, so the application layer, and also diving into a bit of already a bit of the future and so forth. And then finally, we'll have in a panel discussion and a good interaction on other topics, which include developments of the robots themselves and obviously of things such as 5G. Not to forget, and very important, yesterday we talked a lot about safety and robotics and security. Today we'll be having one of the system integrators talking about some of their experiences that they have in some of their client environments on the robots. So just to wrap up basically a couple of the things of yesterday. So in any case, thanks a lot to those who were there, and just to give you a very high level perspective on what has happened. So I think both Tom and Reinhard gave an interesting perspective on how over 2020 there's been quite a significant uptake in terms of interest in robotics, and specifically on the domain of the industry. COVID has moved quite a number of manufacturing companies to speed up the automation, to speed up also the full implementation of robotics on the manufacturing side. In addition, we also saw quite a number of changes from some of the manufacturers try to adapt themselves towards some of the new requirements. For instance, robots are there to support and to help things such as keeping social distance, but also some other interesting aspects whereby, in any case, it seems that the robotics market has strongly increased in interest in the last year. What we've also seen is quite a lot of economic interest, definitely from the side of large industrial consortia that are again developing and buying different robotics environments across the world. So definitely some of those are interesting to see. On the European side, I think a lot of interest is going towards some of the new research activities which are happening, and where also we, in this case, as a community, contribute to the developments of the new strategic research agenda. In Europe, digital is the key, obviously, but also in combination with data. And I think in the next year, 2021, we'll be definitely focusing on some of the developments in that space. Later on in the afternoon or in the morning, We had a couple of interesting presentations, one presented by Jim Gilson from the IEC 62443 committee, one of the co-chairs, and who's also working with REROS, and who shared some of his personal experiences in the space, and also on some of the developments going on within IEC. We gave a bit of thought, and he especially made a lot of effort in supporting some of the questions that came from the audience on how certification takes place and what the backgrounds are of the IEC and how it relates to some of the other international standards. So definitely things to watch over there are other types of developing standards, but at the same time also developments happening, for instance, here on the European side when it comes to, for instance, the machine directive. A lot of regulation is going to happen in 2021, including the changes in the machine directive, but also towards the CyberSecurity Act, where certifications are going to be put in place, and likely also for devices. So we had a couple of interesting discussions later on about whether or not, in this case, we should be more careful about the trust that we put to the suppliers that we have when they provide us with their software. And the supply chain security is important. And an analysis was done by basically the North Atlantic Council in and investigating some of the open source technologies that have shown quite a number of issues on vulnerabilities. Taking that further, we had an interesting discussion about a more wider perspective when it came to cybersecurity, more from a holistic perspective, and different technologies being worked upon for cybersecurity in manufacturing. And the panel discussion had a bit of a conversation about how, for instance, things like security bill of materials, but also basically concepts like shared responsibilities would stand in this world of robotics. And it might become a bit of a challenge. We did notice that there's a lot of importance that need to be paid towards the system integrator, especially for industrial robotics. But what to do if there's no system integrator? Then, and we'll be having a more in-depth conversation about this later on this afternoon when we talk about more consumer types of robotics, for instance, home appliances. There's of course no integrator there, so there a lot needs to be done, much more from the manufacturer side in that environment. So we finalized the day with an interesting series of discussions on safety and security, where we had a very interesting contribution from Jonas Stein from Germany, who's been investigating the impact of systems and cybersecurity on systems on the regulatory schemes when it comes to specifically to complying to some of the regulations and the requirements, and also towards potential litigation or at least liabilities coming out of those. And then we ended the day with a bit of discussion also with one of the European manufacturers, PAL Robotics, where Francesco Ferro gave a very in-depth perspective about the types of regulations that they have to comply to, and also the level of certifications and a reasoning behind this, where it's going much more in trying to defend themselves from potential litigation and abuse. So I think there's a lot of groundwork that we talked about yesterday in many different developments, and providing a lot of food for thought for the next year, and definitely also for future cybersecurity for robotic conferences. Today, though, we're going to talk a little bit further about some of those technologies, and our first speaker today will be speakers. It's going to be a combination of both Leonard, in this case, Leonard Wouters, and Benedict Dierlichs, two colleagues of mine working here in Leuven at COSIC, the research group, which is basically active on embedded security, but also mathematical components of security, and that have been long-standing partners of ELSEC. Afterwards, we'll be having Michael Arguellas talking about his experiences from developments of the SROS, and potentially also to see how in ROS2 security will be further engaged. Then we'll be having the interaction together with Endika from Elias and Ibai Inziarte from Aldakin, the system integrator who has been requested by some of their customers to step in and to help them on analyzing some of the incidents that took place. And then finally, we'll be moving towards the future of robotics. Well, it's not so much the future, it's already out there, of course, integrating artificial intelligence, machine learning, behavioral analytics into the robots is something that happens already today quite often. And so we'll take that a step further by also investigating some of the adversarial attacks or just the adversarial type of concepts that might happen, and that designers of robot systems and we all, as cybersecurity people, together with the robots people, really have to consider also when it comes to both cybersecurity as well as safety. So with this, I'd welcome you again all, and I'm happy to hand over the floor to Leonard and Benedict. Hey guys, are you there?
Yep.
Excellent.
I take over the screen sharing.
How the weather today is in Leuven, but I know about that. So it's pretty sunny. It's about 12 degrees, and I think our friends later on this afternoon from are experiencing completely different about meter of snow. I think it's about off and help us understanding a bit about your experiences in the domain of embedded security. I think both of you are working very deeply in this space. What is embedded security specifically? What do people in robotics really need to start taking care of? And also share a bit of your work in the domain of the household robots and how badly secure they are. Leonard, Benedict, the floor is yours.
Thank you. Thanks for the introduction. Can you see my slides?
Yeah, we can.
All right, I'll bring up the laser pointer. Okay. Hi, everyone. So my name is Benedict, and together with Leonard, we'll speak about threats and security for embedded devices. I think it's quite important to mention that we are not robot people. So we don't deal with robots in our daily lives. We typically deal with smart cards or phones or I don't know, smart locks, these kind of sort of things. Yeah, many of the things we do can be more or less immediately be transferred to your domain, so the domain of automation and robotics and so on. We're not going to tell you a lot about what you should be doing, but instead, what we're going to do is we're going to show you many things that can go wrong and why they go wrong and yeah, which kind of design mechanisms failed for these things to go wrong. And then hopefully that's kind of like a first step for you to, well, to understand why things go wrong and then to build on that and well, try to do better next time, basically. Before we start, I'll say a few words about our background. So we both work at a university in Belgium that's called KU Leuven. Our research group is called COSIC, Computer Security and Industrial Cryptography. We are part of the engineering department, electrical engineering department. That our research group exists since 1979. We are at the moment roughly 80 people, 7 professors, 6 members of support staff, 7 research experts or managers. I am one of those, and then around 60 researchers. One of them is Leonard. Internally, we're kind of organized in different teams. Depending on who you ask, the number varies a little bit, but most of the time we think it's 5 teams that work on various aspects of cryptography and other security mechanisms, all the way from very abstract foundational mathematical research down to real-world applications, implications, and so on. Leonard and I, we are both members of this embedded systems and security team over here. We participate in a lot of research projects, national Belgian projects, European projects. We have also a couple of projects with DARPA in the US, and we have a couple of collaborations with Japan and China going on. Besides funded research, we also have a very active collaboration with industry and with several governments. Our research basically finds applications in domains such as securing the cloud or securing IoT devices, data protection in general, these kind of things. if we have only one thing to mention that we're proud of, then it's going to be the development of the AES algorithm. This is an algorithm that was selected by NIST, the National Institute of Standards in the USA, as the encryption standard. And I'm sure that all of you have maybe not heard of it, but you have used it for sure, because it's very likely right now securing your Zoom connection. It is most probably also securing your Wi-Fi connection from your laptop or from your phone, possibly also your mobile phone data connection, and so on. So this thing has been integrated basically everywhere. There are currently more than 5,000 NIST certified products. There are probably many, many more that use the algorithm and that just didn't bother to get the certification. So that's the one thing that we're very proud of. Our applied research centers around technologies such as various security mechanisms for Internet of Things devices. So one thing that is interesting in many applications is distance bounding. So that's basically a technique that allows us to verify that two objects are no more than X apart. Okay, that can be important, for example, in payments or opening cars, these kind of things. We work on anonymous communications, so that's often related to privacy technologies. Personally, me and Leonard, we work a lot of on trusted platforms. So how can we build electronic devices that guarantee that hardware and software will function in the way that it's intended? We have people working on software tamper resistance and software obfuscation, biometrics, and multimedia security. And these technologies find use in applications such as payment, e-commerce, e-government. So, for example, online voting or electronic ID cards, e-health. So we have people working on security of medical devices. Not yet on medical robots, but medical devices like pacemakers, insulin pumps, all these kind of things. These are, in the end, these are processors. They run some software. And I guess you all can imagine what goes wrong if somebody can tamper with that software. Other applications are around smart grid, smart energy, these kind of things. And obviously also cyber physical systems. And for us, robots are basically part of that category, right? They're connected, they have actors, they have sensors, this kind of things. So as I mentioned, Leonard and I, we are part of the embedded security team, and we actually spend a lot of time in these rooms that you see on the photograph down here. So that's our embedded security lab. And in a nutshell, what we do in this lab is we're very unfair to chips, as you can see on the images here above. And we basically use whatever techniques we have at our disposal to try to extract secret information from chips. So we're kind of playing to be attackers, and we're trying to hack into all sorts of devices and try to extract the secrets, break the security systems. Okay, so for example, on this picture here, you can see that so we can freeze chips, we can heat them up. This is a laser fault injection station, so we can shoot at chips with lasers and try to induce faults so that they will do something wrong. We can give chips electromagnetic shocks, or we can also listen to electromagnetic emanations that are emitted when the chip is doing something. All these sort of things. And we're not doing that because we're bad people, but we're doing that because in order to build a security system, you need to understand how security systems are being hacked. So that's always a double-sided sword, and you need to work basically on both sides in order to really understand the game and to make progress and to make improvements. So let's step a little bit more into the material. Something that I wanted to share is what we call the old security model. So if we say we go back 30 years, this security model would probably be applicable and true. In this model, you basically see some parties that they want to communicate to each other. And for the sake of example, suppose they are computers of your bank and they're sitting behind strong walls and secure rooms, and there are guards with big guns that secure these rooms. And so if anyone wants to attack this kind of banking system, the only thing this person would be able to do is kind of, well, act on the communications link. So try to listen in on the communication, or try to change the communication and these kind of things. Okay, so attacks are only possible on this communication link. And cryptography offers techniques to protect this communication link. Okay, so that's the same thing what happens when you use a secure internet connection. So when that little lock appears in your web browser next to the address bar, you know you're using a secure connection. That's the kind of thing I'm talking about. So this is what we need to do here in order to protect this system. And this is basically something that happens, yeah, on the level of mathematics and algorithms. Today, the scenario is a little bit different, because the devices that communicate to each other, they are no longer these big banking computers that are sitting in secure vaults and so on, but they are little devices that we carry around that are physically accessible, like smart cards, key fobs, RFID tags, access cards, robots, if you will, and so on. So the game has fundamentally changed, because the attacker can also attack the endpoints. He cannot attack only the communication channel, but he can also directly, yeah, attack the endpoints. And so what that basically means is that, of course, we still need to protect the communication channel, as in the old attack model, but in the current attacker model, we basically need to secure everything. We need to secure the endpoints, and we need to secure all the communication links. The attacker in our world of all these interconnected devices is what we call the embedded attacker. And yeah, in this attacker model, the really new thing, or the really different thing, is that the device is exposed to adversaries in a possibly hostile environment. Okay, so the attacker may have full access to the device, yeah, because often actually the attacker may be the legitimate owner of the device. Yeah, so there can be reasons, for example, that I want to hack my own pay TV box because I would like to watch things for free without paying for them. So I have full physical access, or maybe I want to hack my phone. I have my phone here. I can do with it whatever I wish. I have no time constraints, and I have, yeah, all the freedom and time in the world to figure out what's going on and then to break the security. Yeah, as I said, in some scenarios, the legitimate owner can be the attacker. Okay, and so on these images here, we just wanted to show you a couple of examples of how far sometimes people are willing to go for actually achieving very little. Okay, so on the two images on the left-hand side here, you see hacks of the Xbox One. On the left-hand side, you see the same chip as here, but this chip has been opened. Okay, so that you can really see inside the silicon die. So this is the actual chip. Okay, and so people figured out that they need to modify something on this chip, destroy some connections in order to break that security system. So they opened one of these chips to figure out where exactly is that connection that they want to break. But of course, not everybody afterwards who wants to hack his Xbox is willing to destroy it, right? Because you still want to play games, you just want to hack it. And so eventually what came out is a kind of this kind of template that says, okay, you have to draw some lines over your chip following these instructions here, and there will be an intersection point there. And now you have to take a very, very fine drill and drill a hole of a certain depth at exactly this position. And then you will cut exactly that connection that is needed to be cut in order to hack the system. Okay, so this is quite sophisticated. This is quite difficult to do. And all of that in order to save $50 for playing a certain game. Something that is really, really, really important when we speak about security, not only embedded security, but any kind of security system that is the story of the system being only as secure as its weakest link. Okay, so security is always a chain of mechanisms. Okay, and as any chain, where the whole mechanism only works if every link in the chain is strong and works. Okay, and the entire chain is only as strong as the weakest link in it. And here's a very practical example. So this is a picture of a university campus somewhere, I forgot where. And essentially what you see is that here's the road that you take in order to go to the parking. And so here's the parking. And you can see on the image here there's a barrier. Okay, so that's supposed to stop people from parking who don't have a parking permit. And it was a snowy day that day, and you can perfectly see how well the security mechanism works, because essentially it's useless because it's very, very easy to circumvent it. Okay, so that's a good example of a bad way of implementing a certain security system. And I'll stop sharing here and pass over to Leonard.
Okay, so I think now you guys can see my slides. So I will continue where Benedict left off. And as Ulrich already mentioned, there's a supply chain to get these devices to the customers. And I'm going to quickly reiterate how this works for the embedded device. So first, of course, we have to design a device. And I think it's safe to say that if security is not being considered during the design phase, it will probably end badly. And it's important during the design phase to come up with a threat model. So to come up with realistic threats that will potentially target your device. And those threats will then guide the components that you use or the component selection for your product. Now, of course, your device is not going to consist of chips that you all built and designed yourself. You're going to use off-the-shelf components. And you might not always be able to trust the supplier of these components. Or maybe the example code that they provide contains security bugs or vulnerabilities. Now, I understand that in many cases, especially for these industrial robots, security might not be the top one priority. Safety is likely more important. And there was recently an interesting talk on the intersection of security and safety in this regard by Hannes Molson. It's linked in the bottom of the slide. And he handles or talks about how they implemented secure boot in a medical device. Now, once we've designed the device, we also have to manufacture it. And this manufacturing process is usually outsourced. So you ask one company to build a PCB, maybe another company places all of the components on the PCBs, and then maybe yet another company programs the board and packages them, for example. And then the question you could ask is, can I actually verify that the product that I receive from my manufacturer is what I asked them to build? So maybe there have been intentional modifications, and I think everyone knows this story from Bloomberg that's pictured on the slide. I don't think this story was actually ever confirmed, but it would certainly be possible for someone with malicious intent to insert a malicious chip that acts as a backdoor. Now, in some cases, there could also be unintentional modifications. So if a manufacturer decides to help you and replace a chip that you asked for with a cheaper variant, for example, that unintentionally opens a security hole. Now, once we've built these devices, we have to get them to our customers, and we have to provision the device. So the first time we use the device, we might have to generate and store cryptographic keys, and doing this securely is not trivial. Then once we connect the device maybe to a backend server, maybe we want the backend server to be able to verify that the device it connects is actually legitimate. But maybe we also want the user to be able to verify that the device hasn't been modified while it was being shipped to them. So on the right, there's a picture from how the NSA actually inserted chips in Cisco products during the shipment of these products. And you can also ask yourself what happens if someone returns my device. For example, it's very easy for me to buy a vacuum cleaner on Amazon, then modify it and send it back, saying I don't like the product. Now, what happens to this device? Does it get sold again to another customer? Now, once the devices are deployed, we also have to maintain them. Usually by maintaining, we think of software updates. And doing software updates securely is, again, a non-trivial problem that goes wrong often in practice. We also want to do some self-health checks. Has a device been compromised or not? And in some cases, we want a product to be serviceable and at the same time not compromisable. For example, with a car, you would like to give someone access to your car so that they can read out diagnostic information and fix the car without them being able to compromise the car. And in some cases, you might say, for example, for an industrial robot, no one wants to compromise it. I trust all of my workers. And then maybe you have to ask yourself the question, what if someone gives one of my employees a USB drive and $1 million? Are you sure they will never plug in that USB drive? Now, once we're done with the devices, maybe they've served their lifetime, they have to be disposed of. Or maybe a device was compromised, and can it then be revoked? And if it's disposed of, usually these devices will inevitably end up on eBay. For example, I found a Mir robot on eBay quite easily. And then the picture on the right shows some vehicular components. So these are basically the media control units from Tesla vehicles. And these were replaced in vehicles. But people bought these basically secondhand on eBay and were able to extract personally identifiable information from them. Now let's look at a more practical example of what can go wrong. So these are, I think, devices you all know. They're basically vacuum robots. So you could say that in some way they are similar to robots that are being used in industry. In this case, they drive around and they run Linux. But they also have cameras, speakers, and microphones. And this is, of course, a very convenient feature if you leave your kid at home and you still want to communicate with them through an app through your vacuum cleaner. I'm sure a lot of people use this feature. Now, if we think about what's inside of one of these devices, we usually see these three components. So we have a system on chip, which is the main processor. We have some volatile memory on the left and some non-volatile memory on the right. Now, during the development, the designer or the developer will usually interact with this device using debug interfaces that are sometimes left open and that we as an attacker can also use. Now, the main interesting component you could say is actually the non-volatile memory because it stores the operating system and the file system and all of the programs that are run by the device. So if we are able to access this, we can learn a lot about how the device works. Now, if we look at this inside of an actual vacuum robot, we can see in red the big system on chip, the main processor, which is connected to a DRAM chip. And you can actually quite easily see that this is a DRAM chip because there are these squiggly PCB traces, whereas the flash chip is connected with just straight PCB traces. Now, if we zoom out a bit and we see all of the parts involved in the vacuum robot, we can see the motors that drive the robot. We can see the green module that we looked at earlier. We can see a UART debug header. That's quite interesting. We see the camera, but then there's one small, very interesting component to see on the inside of an embedded device, and that's this micro USB connector. And now, as it turned out, once we plugged in a USB cable here, we were able to run the command adb shell and get a root shell on the robot. So now we have already full control over the robot, but we still require physical access to one. Now, to figure out how this robot communicates with the rest of the system, we built a setup that looks like this. So we have our laptop that connects to an Android phone that is running the companion app of the robot. We have a vacuum cleaner that connects to the Wi-Fi network, and I then route the traffic through my laptop before sending it back to the cloud. Now, using some off-the-shelf software, I'm able to sniff and modify all of the traffic, and in that way figure out how the system works. So what we figured out is that the cloud will send commands to the robot, and it will specify which robot command is for using a robot identifier. And the robot, when it receives a command, will check that the auth code is correct. So it's basically like a password. And it will then check the command that it received. So in this case, command 127 means perform a software update. And now to perform the software update, you also have to supply a URL where the robot will download the software. Now, because we have compromised the robot, we can also look how this software update works internally. And so what we figured out is that basically the robot will use a program called wget to download a firmware binary and then install it. Now, because this, the way this is implemented, it's vulnerable to an OS command injection attack, which basically means that we can inject extra commands in this malicious URL. So we basically tell the robot to download a software update here. Then we make the software that we've sent it executable, and we execute it. So what does this mean? It means that I can enumerate robot identifiers. I can enumerate the passwords that the robots require. And then we can send a malicious update command, and in this way, basically compromise every robot that this manufacturer has made. And this is what's called a BOR attack, or a break once, run everywhere. Now, as you can imagine, we can take control of all of these robots. They have cameras, they have microphones, they have speakers. So this means that you can do virtually anything you want with your own robot network, your own malicious robot network, basically. Now, I see I'm running out of time, but there's one more thing I would like to show you, and that's some research that we did recently, in which we looked at basically the keyless entry system that is being used in a Tesla Model X, and we built the device that's shown on the screen to basically exploit some flaws that we identified. So I'm going to show you a video of how we execute this attack in practice. So this is in front of our office. And maybe you'll recognize Ulrich, who maybe naively parked his car in front of my office. And so I noticed that he parked his car there, and using the device that I've built, I walk outside. I walk up to his car and I read a few numbers from his dashboard. So basically the VIN number. And using that VIN number, I can make my device believe basically that it is Ulrich's car. We can then walk up to him and we can instruct his key fob to wake up. Once it's woken up, it's basically a Bluetooth device. We can connect to this Bluetooth device, and we can again do a malicious firmware update. Now, as it turns out, the key fob doesn't properly verify that this is a legitimate software update made by Tesla. So I was able to push my own software update, and in that way, basically ask the key fob to give me some valid unlock codes. Now, using these one-time unlock codes, we can go back to the car, and we can then broadcast these codes using Bluetooth Low Energy, and then in that way unlock the vehicle. So we can open all of the doors, and that's fun, but of course it's more interesting if you can also drive away with the car. And to do that, I looked at how Tesla would pair a new key fob basically to the vehicle. And we figured out that there's a few flaws in how they do that. And this basically allows me to pair a slightly modified key fob to the car. So we open a panel in the car that gives us access to the diagnostic connector. We then plug in our tool to that connector. And then using my phone, I can basically pair a new key fob to the car. And then at that point, the car will believe that there's a legitimate key fob in the car because it's paired to the vehicle. And it will then allow you to start the car and drive off. Okay, so with that, I think it's time for me to conclude this presentation and give the word back to Ulrich and the next speaker. Thank you.
Leonard?
Yes?
When can I get my car back? All right, thank you guys, thanks a lot. And thanks for doing this. I think we were definitely interested about the robots and the vacuum cleaning robots. And I hope you can build a botnet out of it that's actually going to be useful in this case, that does not drive away in front of my face, but that's actually going to do something in the cleaning of my house. So, but no, great presentation. Thanks for the overviews to the both of you. I didn't get any specific questions from the attendees, so a couple of ones from my end. So you don't have to be robot engineers. In your case, the whole point of this is really to bring together people from cybersecurity land, from the industry, as well as people from the robotics land, and trying to figure out, okay, how does this need to improve towards the future? So in that respect, my question to you, because that's really what we aim to do, is work with the manufacturers and with the system integrators and the consumers to improve. So according to you, what needs to be done in order to do this type of improvement? What types of technologies maybe can we look towards, also maybe towards the future, that would help us in this way? Also from the embedded side, of course, and from the components. Are there some things that we need to watch out for? Are there things that we need to take care for? So it's a bit of combination. So any thoughts?
So one thing that maybe is an issue because we don't have a strong background in robotics is that we don't fully understand the threat model for these devices. And as I mentioned in the slides, it's difficult to say how exactly you should design a device without knowing what how it will be used exactly and what the safety constraints are, for example. So in that regards, I think it's still a difficult question to answer without that specific background knowledge.
Okay, so that's something that we can work on without a doubt. But there are things like components which are being added into the chipsets that could help out the developers of the and basically the manufacturers of the robots today. Some of them are working towards IoT connected robots, cloud connected robots. Of course, many of them are still very much on the traditional domain, PLCs and controllers. And so therefore basically the threat model is diverse depending on the type of robot, on its use case, as we talked about yesterday as well, the way it's implemented, and what it's actually being used for. So in many cases, there's a sort of an avoidance of connecting it to the net, trying to isolate it, but therefore forgetting that sometimes the management execution system of the robot or the controller is could be connected, and so there might be a bastion host that's working as a sort of an intermediate. Sometimes there are industrial firewalls which are trying to avoid this, but at the same time, of course, we know that there's routes that we can get in there, either through Wi-Fi channels, wireless channels, or the way that you showed also with the domestic robot. So I think that the question is much more also from a generalistic perspective. So maybe not only from the robot side, but are there things like, I don't know what, multi-purpose type of microcontrollers that you see that have security functions included that should maybe be looked into by the manufacturers and should also maybe be already further enhanced.
So two things that are really, very general, as you say. The first one is, of course, if a robot is not connected, then it has a very small attack surface, because I mean you can only attack it if you actually are near that robot. If you put the thing on the internet, well, then you have the entire planet against you. So while of course we completely understand all the commodity and usefulness of putting things online and connecting them and so on, I think it's very important that people are also aware of the downside of just vastly increasing the attack surface and the number of people that they will be exposed to. So that's one thing. Another factor, the second factor that is super generic is what Leonard said in the presentation, is this, break one, attack all. So that's a very typical design mistake, that if a system is designed such that once you have broken the system, then you have basically, you break one robot and afterwards you dominate them all, right? So and a system should always be designed that breaking into the second robot is as difficult as breaking into the first robot. So that just, the attack doesn't scale as much. So it becomes much less, profitable or whatever for the attacker to break systems. Yeah, because that's maybe also something I should say. It has to be basically clear from the beginning that it's impossible to build a 100% secure system. Okay, that doesn't exist. It's the same with all kind of physical systems, like physical door locks, for example. Yeah, every physical door lock can be opened by someone who's good enough at doing that. And the question is always just how much effort and expertise and money and whatever is required for breaking a system. So the game that we're playing, or the game that anyone can play at best, is just a game of trying to make it hard enough, so that the benefit of being able to attack something, just doesn't pay off. And the problem here is that sometimes it just doesn't scale, because sometimes the attacker's motivation is not money. Yeah, like in the Xbox hack, I'm sure that tons of time and money went into that, and all of that for just saving 50 euros, so that to not have to buy the game. Yeah, so this is much more of a interest, curiosity kind of motivation, and that's hard to put a money value on it. Huh?
Yeah, what's the value for a guy that's doing his PhD at COSIC to steal a car? So it's the same thing. No,
but if I imagine I see some industrial robot somewhere, and then I don't know, somebody spends a year on trying to break into it because he just wants to see how the thing dances. It's hard to say, oh, this attack costs 10,000 euros, because it's very hard to measure that.
Yeah, true. But it does pay off if you're capable of basically ensuring that one of your biggest competitors is suddenly no longer capable of producing those COVID vaccines.
Of course.
We know that the price is 1.4 euros. So
yeah, of course.
So there's a couple of things to keep in mind, but absolutely. All right, guys, thank you very much for your contribution. Highly appreciated, and I hope to be able to see you back in future CyberSecurity for Robotic conferences. So I'm sure that we can find a nice robot for you to be challenged on, Leonard, and I'll bring it along to the labs, that we can maybe next time have some other interesting video material to show.
Don't you have a kitchen robot, Ulrich?
I've got plenty of robots for you to play around with, so don't worry about it.
Excellent.
Right, guys, thanks a lot, and have a nice season then.
Same to you. Bye.
Mikael, nice to see that you've joined as well. Good to have you here, and great to move up from, let's say, the embedded systems into the world of the robot operating system, the SROS. So Mikael, I think the time that you participated for the first time in SROS, I think it's been probably a couple of years, but in the meantime the world has moved on. ROS has moved on. There's now ROS 2. There's many more, which is, I think, a good thing. Companies and manufacturers that are endorsing also ROS. So I think it's time to give us a bit of an insight on how you came up with SROS, together, of course, with others, and of course also how you see the world moving along. Thank you very much for joining in. How are you doing?
Thanks for having me. Sound is very bad on my side, so I would just like to make sure that you can actually hear me well.
We can hear you perfectly, loud and clear.
Okay, that's awesome. So yeah, I'll share my screen, and I'll show like a couple of slides on like the history of security in ROS and what has been done in recent years.
Superb, thank you. All right, can you see this well? Yes, we can.
Perfect. All right, so my name is Mikael. I've been working with ROS for quite some time, and I've been fortunate to be paid to actually work on open source software, and part of my time was spent on like thinking and designing things to be able to make like ROS a bit more secure. And so I'll just give a bit of an overview of like what is ROS, what is ROS 2, what have been the initiatives in the past to actually make ROS more secure. And then like, okay, what changed with ROS 2? What is this thing that we call DDoS security? And then what tooling around that has been built in ROS 2? So then we can actually like discuss like what it can do today, what it should be able to do in the future, and what are the current limitations. So ROS, I think many people have seen that slide many times in the past. So the idea is that like ROS is actually like not an operating system, it's an ecosystem. It started by being just a way of communicating between processes and between machines. And then a lot of like tools and capabilities, amazing algorithms, and a bunch of packages released by people all over the world to make robotic systems more complex. And so ROS has been fully designed so quite a while back. So in 2007 it started, and it was mostly focused on providing software to be able to build research robots. And so at the time, robotics was very different from today. And so it was this type of like big single unit robot that would have like a lot of power on board, complex kinematics, awesome network community, everything on board as well. And everything was built around this idea of having what like a ROS core, what we call the ROS master, which was like this process that would be like basically brokering every communication happening within the system. And so in ROS, you would create some components that you would call nodes. And for nodes to be able to communicate between each other, they would have to like register themselves to the master and say, okay, I'm offering this type of capability. And then when another node is interested in leveraging these resources, would ask the master, okay, who can provide me that? And then the master would take care of like saying, okay, node A, you should communicate to node B and like create a socket there and discuss on this. There were like a lot of issues with that approach. One of them being that this ROS master is a single point of failure, but other things were just like security was not taken into account at all to start with. The goal was for it to be dynamic, easy to use, very modular, and so security was left on the side. So all communication is like clear on the wire. Any new node can like just spawn, contact the master, and be connected to the rest of the graph, get every information of the entire graph. And then anyone can send any information to the master, so we can actually impact the entire system. And the only like workaround that existed at the time is like, oh, if you want to make it secure, you should put your ROS network behind a VPN or like some kind of like enclave system, and just say, okay, as long as you're inside that capsule, you're fine. But then it also means that like anyone having access to that network can still do all the things that were mentioned above. And so several groups have been trying to like bring a bit more security into it. So I'm just mentioning like some projects here. They're not the only ones. One of them was called Secure ROS, with the goal of like using IPsec to be able to like managing, like everything would be done over IPsec. And so it would bring all the security features of IPsec. And SROS was another approach that has been developed mostly by Morgan Quigley and Ruffin White, where the goal was to be able to bring both like network security, so bring TLS, PKI, authentication, access control to ROS, being able to like define access control policies and enforce that like nodes could only do what was defined in these access control policies. And then a lot of tooling around that to be able to like auditing running systems, profiling a given ROS application to make sure we can cover all the permissions that are required during runtime of a system. And then also more of like a process level security, which would be like providing, for example, APAMO profiles for basic ROS applications so that people can leverage these profiles and build their own on top. But one issue that exists with this project, but like basically every project trying to bring security to ROS1, was the fact that like it was still trying to bring security as an afterthought to a system that was like not built for that. And which has all the drawbacks of like it had to break a lot of API, and as a result, it could never be integrated in the trunk of ROS. So it was always like a fork of ROS that people had to do a lot of manual operations to be able to leverage them. And so that showed its limits, because for usability for users and people building products, it was like pretty complex because they had to keep that fork up to date all the time, and so it was pretty difficult to use. And so that's only like one of the many things that was limiting in ROS 1. The world of robotics changed a lot since 2007. A lot of things have appeared, like drones or other like robotics platforms and swarm of robotics platforms. And so a lot of things that were considered as like valid assumption or hypotheses for us are not really valid anymore. And so as you can see on this slide, we have like more and more multi-robot systems, like more distributed systems, smaller processors, smaller resources, limitation in autonomy, and limitation in network quality and connection quality. And so many of these things are not really compatible with how ROS was built. And this is why Open Robotics, the company or entity that is like stewarding the ROS project, started to work on a new version of ROS, instead of trying to like break the low level of ROS and impact a lot existing users, start from scratch another project to try to address all these concerns. So there is a link here. I won't go in details like what are all the challenges that were trying to like be addressed by ROS 2. But the idea is to, instead of having all the plumbing that is custom and made by ROS developers to come up with their own communication protocols and everything, use instead standards like industry proven communication protocols. And so in this case, the default one used by ROS 2 is DDS, which is a standard built by OMG, and allow ROS developers to focus on like the robotics part of the system more than the communication part of the system. And so one of the advantages of that was to also like try to like focus time and effort, but on like the things that are relevant, but also try to simplify the software stack, which right now in ROS 1 was really like siloed. So you had like a full implementation in one language, a full implementation in another language. And so you had like different bugs here and there, and you had to fix things in multiple places and things like that. And so the goal for ROS 2 is to keep people developing like ROS code at the higher level. And this would like go all the way down to an implementation of that communication standard that would take care of all the communication, discovery, serialization, transport, quality of service, all this. And one of the advantages of that is it allows to, because it's a standard protocol of communication, the API is also standard, and the wire, like the shape of the messages on the wire is also standard. So you can actually like swap and use like different implementations of that communication protocol without impacting the rest of the stack. And to be able to do that, the goal was to like basically develop a middleware API that would be like standard for all of ROS, and everything that's below the middleware API would be specific to the transport, and everything that's above would be specific to ROS. So I'm just going to skip over those, but so we just have to do like small implementation packages to be allowed to plug different implementations and connect them to the ROS stack. So one of the advantages of that is first, it allows to simplify API at different level and enforce like better abstraction throughout the stack, which is like not necessarily related to network security, but at least like allows you to have a clear separation of concern of like what functions should be where in the ROS system. And it also allows to have like this common layer of like the ROS client library, RCL, which will be shared by any implementation of ROS in specific languages above. And so we have to focus only on one part to do things right there, and then everyone can benefit from them. And so then it's fairly easy to provide support for different languages on top, which is basically all the features provided in C at the lower level, and then you just have to like wrap it up in various languages. And so now the question is like, how does that play with security? And so for ROS 2, one of the concerns was like to have the same issue as in ROS 1. If security comes into play late in the development process, the same issue will happen again. We'll have to break every API and impact users significantly or make it very hard to use. And one of the advantages of using like that standard protocol, like communication protocol, was that people who designed that standard also thought of like how to secure the communication. For them, it also came a bit as an afterthought because like that security standard came out quite a bit after the standards of communication itself. But they had the benefit of having like specified everything in an official specification before we started implementing it. And one of the things that's convenient with that is that so they standardized both like the functionality of the various parts of what they call DDS security, and standardized both the API and the type of like plugins that people should implement to provide various security features. So in the DDS security spec, they outline 5 different plugins. One of them, which is basically the basis for most of the other one, is authentication, which is basically defining how a system, like how nodes within a DDS system and so a ROS system should be able to authenticate with each other. And we don't have like this single authentication that was happening like in ROS1, where like basically everyone had to speak to the master. Now we're talking about like discovery of peer-to-peer participants that have to all like validate that they are all allowed to be there. Then there is a cryptography plugin, which basically defines API on how to perform cryptographic operation, which can be like key signing, verification, encryption, all these kind of things. And the third plugin that's of interest here is the access control plugin, which builds on top of the other ones, and which is how can we specify which resources a given node in the system is allowed to access and is allowed to provide. There are additional plugins that are considered as optional in that specification. One of them is the logging one, so how to log in a secure way all the security events. And another one, which is like data tagging, which allows to like actually watermark various messages to provide extra information that can be verified by the receiver as well. And so if everything is already provided by DDS, like what is ROS2 doing for security? There is nothing to be done. And well, it's almost the case, and that's actually great news. So the main goal of security in ROS2 is to make these functionalities and features available for ROS users in a not too cumbersome way. And so there is a link there, like how these things are connected together. But the main thing is to provide in the low level of ROS ways to instantiate these various security plugins and provide them with information they need to be instantiated and functional. And then on top of that, the tools that we call as ROS2, it's a set of like small like command line tools that are really like convenience tools to help you analyze your system and then like generate all the material you will need to have a running secure system. And so it can do various things. One of them is to be able to generate keys and certificates for every component of your system, define a file format that's including ROS semantic into it. And so instead of speaking like DDS specific vocabulary, we would define things like, okay, that is a topic, that is a service, that is a ROS action, and be able to define access control policies with that verbiage. And after that, so we have the ability from this information to generate and sign all the files and configuration files that DDS security would expect in the DDS world. And then we have small utilities on the side, which are more for like auditing a running system, or like being able to say, okay, let me run my robotics system for days and have this thing monitoring it to be able to like estimate all the resources every component of my system needs access to, even if it's ephemeral. And so where does that live in the ROS stack? So one of the main goals was that like to be able to enable security, ROS users should not have to change how they write their code. And so everything is being done in like the lower level, and mostly in the place that is like transport specific, so where DDS security actually lives. And so in the implementation of the ROS middleware interface, that's where the decision to like instantiate plugins would happen. And then the actual like implementation of these plugins will live within each of the DDS implementations. But in order to do that, we do need to like be able to retrieve information and give it to these lower layers so that they can configure it and instantiate the plugins. And so right now, and some things that we will discuss later on, this is done mostly with environment variables that are set at like before runtime, basically, which allow to specify, okay, should this, like all the processes that will be spawned in that shell use security? What kind of security strategy should they use? Are there some parts that like could be unauthenticated, but are okay within that system because they're like not relevant for the core part of the system? Or should they like all be authenticated and using security? And finally, what would be basically the road path? Where would I look for the security artifacts to configure my system? And so once this is done, we can actually like retrieve where all this information is, extract that information, retrieve exactly the specific security artifacts that are needed by the plugins we want to instantiate, and actually instantiate them. This is not really relevant. This is just code on like how this is instantiated after the fact. And then CSfR2020 provides us with policy files. So that's what I mentioned earlier. We define kind of like a syntax for ROS users to specify what the access control policies are for their system. And so we chose an XML-based representation, and this allows us like various things, including like ensuring that everything is valid, but also allows us to like include others like XML parts. So it's basically just based on X include, so that we don't have to like repeat ourselves too much. And so here we can see that like we are defining that each profile, which is basically the equivalent of like a ROS node, would start by including all the permissions that a basic node needs, and then declare what extra policies it needs. And so here we have a few access control rules. So we can see that we define services, which are like ROS services, and this will then like be expanded on like what a service represents in the DDS world. And the same way we can define topics, saying, okay, this node needs to be able to publish on the chatter topic, or this node needs to be able to subscribe to the chatter topic. And then CSfR2020 is extending the existing ROS2 command line tools to basically provide a new verb that is ROS2 security. And this provides a various set of commands. And so here I'm presenting kind of like this meta command that people can use, which is now that we have like a policy file with all the information of our system, we can actually say, okay, go ahead and generate all the artifacts I need to be able to enable securities for that entire system. And so this will just take like a key store path, which is basically where on the file system are the artifacts going to be located, and the policy files that we showed earlier, which are defining the access control policies of the system. And based on that, the tool will create a key store, will generate a root, like a certificate, a CA certificate, and this CA will then be able to like sign every artifact for any component of the system. And so we would create key certs for every single participant or every single node in the system. And based on this policy information, we would also generate like the DDS specific file, which lists all the permissions that are allowed for each node. And we would sign that with that same like authority, so that this can be like ensured it's valid and comes from the right authority. So this is a short example of like what the resulting DDS permissions file would be. And so here we can see we have like extra information that's not like ROS specific. And so we would say, okay, in which DDS domain would that apply? with DDS partitions and things like that. And then our specific ROS permissions would be translated into DDS topic. And so here we can see that like we can publish on the RT my pub topic, and we can subscribe onto RT my sub topic. And so then we can like try that in practice. So in this case, we have defined policies on like what a talker node could do. And so a talker node could publish messages on a chatter message. And here we try to run that talker node, but we say, oh, instead of publishing on the chatter message, on the chatter topic, you will publish on the my chatter topic. And here we can see, oh, actually, like you cannot create a node with that, because as soon as you try to create a publisher with this rule, it's going to be checked against the permissions that have been defined for that node, and it will find it's not allowed to publish on that topic and prevent you from creating the publisher. And so CSfR2020 provides a lot of different bits. One part is like integration in the ROS stack to be able to instantiate DDS security plugins. And on the other hand, provide tools to help people more easily configure and use security for ROS system. But as you have seen before, there are several things that have like pretty limiting. One of them is like the fact that in order for users to not modify their code, right now it's relying on environment variables to retrieve all that information, which is not necessarily really convenient, both because environment variables are not all systems have environments to run in, and that environment variables are not like the most robust way of specifying things. Another limitation is that like the key store is stored on the file system and the keys are stored in clear text, which means that anyone accessing any of these directories where the keys are stored could actually like get the keys, and which is obviously something you wouldn't want. There is currently no support for alternative key storage mechanism. Most DDS vendors provide only one plugin, which is their default plugin. And so it means that like you have little options on how either authentication or cryptography is being done. So if you have specific requirements for your system, you may be a bit limited for that. And while CSfR2020 gives you a lot of granularity in a sense that like you can specify access control policies on a per topic, like per node and per topic basis, it doesn't allow you to specify the type of protection you want for all these components. And in a regular robotic system, you would have some parts that are much more critical than others, and some parts that would require more privacy, and some that would require more integrity. And so you would like to be able to choose between those. And so, for example, you could say that like some type of commands, like, I don't know, control commands, are not critical on the privacy side. It's not really a problem if people can see what type of command is being sent. But for sure, you want to make sure that every command is received and hasn't been tampered with by anyone. It has to come from the right person and be unmodified. And so we would like to be able to say, okay, these topics need to be signed, but don't need to be encrypted. These topics need to be encrypted, and these kind of things. DDS security supports like the way of revoking certificates and revoking keys. And so basically, this is not exposed currently by CSfR2020. So for people that have long-running systems, it may be limiting. Then we have some more like logistics issue, in a sense that like if you have big nodes or participants that do a lot of things, the fact that right now in CSfR2020 we try to have the most precise access control policies means that like we have a lot of rules, and we're actually hitting one of the limits of the transport, which says that like the size of permission files that are like signed and sent on the network so that everyone can make sure the other node is allowed to do what he wants to do, we're actually hitting a size limit there. And finally, like SROS2 has been focused since the beginning to provide access to like network security, so just how to encrypt communication and manage the network, and nothing outside of that. And so everything is for all the OSs and really focused only on the networking libraries. But we could think of like providing other security utilities like a part of SROS1 was doing. So if we wanted to do process security, we could provide like APAMO profiles or things like that, but these tend to be OS specific or like platform specific. And so it's a bit harder to generalize these kind of things. And so future work, like, as you can imagine, there is a lot to be done. So of course, trying to address all the things that have been previously mentioned, provide more granularity, more robustness, more secure storage, and then also improve or add tooling. So the tooling that is like existing today, we have some like audition tooling that allows you to like capture everything that's happening on a ROS system. But this is more working as like a snapshot, so which is like basically at a given time, you can know all the connections and all the permissions that are required for the system to run. But in ROS, there are a lot of connections that are ephemeral. We have a lot of things like ephemeral services that just do like one request once and then disappear. And so we would need this audition, like tooling, to be able to like capture all of these over a long period of time to provide you the full set of permissions your system needs to run. A cool work that's being done currently is to actually integrate security with the rest of the ROS tooling, so make it like more easily to use security and still be able to use other tools. And one of them is to actually like do all these key generation, storage, and sharing like on the fly. So being able to use like ROS launch, which is a way to launch a set of nodes on an entire system, and to look at all the needs of all the nodes that will be spawned and generate exactly what you need, keys and permissions file, so that that specific system can be run. And then we would like to experiment and play with the tooling on larger sets of systems, because right now it's not used on like deployed systems a lot that I know of. And so would like to play with bigger systems to have an idea of like what other limitations we're going to be facing, limitations similar to what happened for the size limit, the site size limit. And of course, like many open source projects, we will need to write even more tests and write better documentation. And that's a given for many projects. And so I think I'm almost out of time. So I would like to just give a few links there. There has been quite some discussion and many efforts online in that matter. So this is just a subset. We have a group of people that are thinking of these issues and trying to commit time to improve the various parts, which is the ROS security working group. All the meetings are open, all the contribution or feedback is welcome. And so feel free to join these meetings, share your thoughts, share your use cases, share the limitations you face, and everything that comes to mind for robotic security. And finally, I would like to really thank people that have been working towards that goal for a very long time. And of course, this list is far from being exhaustive, but Open Robotics and the ROS Security Working Group or like their continued work on that. Morgan Quigley and Ruffin White that have been like basically pioneering this SROS work. And then people from Canonical and other groups that are working like on a daily basis to improve SROS2. And mostly, and I think a lot of them are in the conference today, everyone that has been working on improving like security for robotic system in various areas, because like securing the communication is only a tiny part of securing a robotic system. And so I'd like to thank everyone for their efforts. And that's going to be it for me for today.
Thanks a lot, Michael. That was very enlightening. And Ruffin is also here listening in. So I'm pretty sure that the Oscars gratitudes have been heard quite clearly. So thanks a lot. I think that was very insightful, very good overview, both for the people that were not very much into ROS or into basically even robots, but much more in security. They might have some thoughts and considerations which we can work on. My two colleagues from earlier on, both Leonard and Benedict, will definitely have a bit of an eyesight there as well. Given a couple of questions, we have a question coming in from Cameron, who posted on the chat to you. What's the vision for SROS2 regarding certificate authorities, certification authorities? So for instance, with distributed robot swarms. Yeah, I think what you also pointed out to was the larger systems. And can you also give a bit of a better understanding of what you mean with larger systems? Is it the swarm like of larger system that you have in mind, or is it just a larger robotic system? So what do you mean with a larger system?
Yeah, so for larger systems, there are a couple of challenges arising. A lot of them and most parts of the system will lose connectivity and gain it again. And so several questions come to mind. First of all, having a single certificate authority is something you can't really have in general for a large system, because you have various components of your system that you won't have control over the keys that are stored in there and the certificates. So you actually need to have a better way of managing your full chain of trust. So you would have intermediate certificate authority for various parts of your system. And then for the fact that basically when your system would go offline, it would not need to establish new authentication or verify new things, in a sense that the connected graph of that specific part of the system is done, and so now they can actually communicate. And then the question is when they come back online or meet other part of the system that want to communicate with them, at that point only, they need to be able to challenge each other and validate that they are both allowed to talk to each other. So I guess there are different issues to address in that matter. Well, I can't hear you anymore.
Yeah, that happens if you put the mute button on. I knew that it was going to happen at least once today. On the question about the SROS2 regarding of the certificate authorities.
I'm sorry, Rick, I can't hear you at all anymore.
Okay, so on the chat you can see the question from Cameron. What is the vision for SROS2 regarding certification authorities?
Okay, so I guess I'll try again. I'm reading it right now, and so yeah. So part of the thing is that you would have on various robots intermediate certificate authorities that would be for sub parts of the system, and that would know of the higher level certificate authority, and so they could still ensure that when you receive connection, you can make sure that the thing you receive has been signed by the certificate authority that you recognize as a higher level certificate authority. So you wouldn't need to be fully connected to the highest level certificate authority at the time of connection. But I'm not sure that's answering the question.
I think you are to a large extent, but he's definitely concerned about how to work, for instance, when you have a swarm which is not publicly connected to a CA, how it needs to then get the basically the certification going. But maybe it can also happen through a mesh activity, or basically if one of the components in the swarm in the system receives the authorization, that it can act basically in itself as a certificate authority. But that's maybe work for later on.
Yeah, I'm sorry, I can't hear you. Like my sound is very bad, so that may actually be changing for the roundtable because like I can't hear the audio well.
Okay, right. In any case, no worries at all. I'll see you back in a couple of minutes. We'll move on. In the meantime, in this case, I would like to invite both Ibai Inziarte and Andika. Ibai, you are part of a systems integrator in Spain. I think you have mainly clients also in Spain, and you have been working quite in depth, I think, with some of your clients, specifically in relation to some of the incidents that they have had. So please do enlighten us a little bit about some of the works that you have ongoing, and let us know how we can learn from those experiences.
Hello, I have problem to. Can you hear me?
Yes, we can.
Yeah, I have problems to share my screen. I don't know what's.
Okay, so we have a backup therefore. Let me try to find the backup in this case. So maybe you can explain in the meantime a bit about some of the activities that you do as within the company, and how it relates to some of the discussion that we might have.
Our company is called Aldakin, and we are an electrical engineering, and we do electrical engineering and robotics. Okay, and
Ibai, you're still there. We can't hear you now.
Hello?
I think we lost Ibai.
Yeah, no, I'm back. I'm back.
Okay,
now
yeah.
You can see my presentation.
Yes. Okay. You've been working in the back end on trying to, in the meantime, I was just launching your slides as well, but yeah, you have them now. You're good to go. Go ahead.
Okay. My presentation is about our very little experience with cybersecurity in robotics. It's little, but with I don't know how to say big or critical consequences for our customers or possible
significant.
Yeah, significant consequences for our customers. But I'm going to start explaining our company a little. We are a group of 6 companies founded in 1986 with 2 business units. We do electrical engineering and robotics and automation. And currently we are working around 160 people, okay? So the first use case, I'm going to start with the first use case. First use case was a very strange robotic cell for us. An hospital asked us to develop a robot for brain retraction. Brain retraction is the operation that you can see in this video, okay? And it's in order to control the force and the movement during this operation, because now it's done manually, and you have to stay in this way a lot of time, and it can be because the human does not control his force or his own force in a long time. So we developed this, and during the development, during the testing in the operation room, not with humans, okay, not with humans, the hospital was hacked. The hospital that we were doing this test was hacked. And we start talking with the surgeons and the people that we were in touch. What would happen if not only our robot, because there are other robots in the operation room. What would happen if this equipment will be infected? And the main thing was not that they don't, I mean, the surgeons didn't know anything about cybersecurity, of course, but even the IT department of the hospital, when they thought about cybersecurity, they were thinking about IT, about PCs, about desktop, about laptops, about the images of the MRI, CTs, and those things. They didn't think about the equipment. And it was really, I was really amazed, because I thought, if this equipment is hacked or infected or whatever, it can be, someone can be dead. So this was our first contact, and it was just several years ago, and nothing happens. That's my experience that I have said. It's little, but when nothing happens, the customers of the possible users of this technology don't do nothing. So in our second case was mostly the same in another context. It was a customer from us who has a pick and place robotic cell, and approximately every 2 months the Ethernet card was born. Every 2 months we tell them, can you replace it? Just replace it and check it. Maybe it was a production error in the card, and just replace it, and if it's okay, nothing is happening. So 2 months later, it happens again, and we call the customer support of KUKA. It was a KUKA robot, and we were trying everything, and we didn't see any reason to that problem. When we touched the car, it was very, very hot, and we see that something was happening, but we didn't see anything in the robot was working correctly. Apparently there was no problem. And after one day, after trying everything, someone says, why don't you scan the control system with the antivirus? And during the scanning, we realized that the robot was infected. But as in the previous case, after scanning the robot or the CPU of the robot, the problem was solved. Again, the company didn't do anything because nothing happened. So this is our main experience with our customers, because when nothing happens, we do nothing. But in the last use case, we have a regular commercial consultation by a company, and instead of asking us about the price, about the cycle times, about the deadlines, they ask us rare questions. and that we didn't know how to answer. What happens if I connect to a network? We said nothing happens. What happens if a swarm goes into the robot? And we didn't know why they were asking us these things. And later we were informed that a collaborative robot of this company was hacked with significant consequences on a worker's health. So that was the first case that we see that a customer was really worried about the consequences of hacking, of cybersecurity in robotics. And then we meet through LinkedIn, Íñigo from Alias Robotics, and we start talking about these things, and we tell them to start an alliance or something like that to offer their services to our customers, because we don't know anything or almost anything about cybersecurity in robotics. And our customers, most of the customers, they don't even know that it's a real problem. So that's why we started. And this company, now they have their own service, I don't know with what company, of cybersecurity, but we realized that it's a really important problem, or that it could be a really important problem, especially in collaborative robots, because there is no fences, and if there is no fence, the human can have an injury or something like that. And this was all of my whole presentation. I would like to thank to Trinity European Project also, and to Endica as well, to offer me this opportunity to join this conversation or explanation.
Thank you very much, Ibai. Thanks for the sharing of the experiences and also of the incident. I think it was very interesting. We have a couple of reactions coming in from some of the attendees. But maybe before we hit the questions in the Q&A, Endica, good afternoon to you too.
Good afternoon, everyone. Good morning, everyone in the US. Thanks, Ibai, for the very nice talk. I think it was fantastic to have you today speaking openly about this problem that we are witnessing once again. And it's been fantastic hearing you.
Endica, you have worked already for quite a couple of years with Alias Robotics, and you're leading the team now. We've seen yesterday a great presentation from Victor, one of your colleagues. And so my question to you is there's a reason also why you're here, of course. You've been helping out Aldakin, as was indicated by Ibai. How can companies like system integrators like Aldakin actually work on these types of cases? Because as Ibai indicated, the customer, when it's a group of basically doctors, experts in their space, don't know basically anything about cybersecurity, don't know really how they need to program the robots, they don't even know how to work with or what they should expect, even in terms of cybersecurity means of robots. So on the experiences that you now have, what is typically the better way for system integrators like Aldekin to deal with these types of issues, which highly likely will be seeing popping up much more often? And I think taking it to a next level, yesterday we had at the very final moment a very interesting comment made by Tom. What if there's no system integrator? So what should happen then? And also ask further along, of course, to Ibai.
So I'll take it if you don't mind, Ibai.
Yep.
Short answer is by finding the right partners. Of course, this is but this happens pretty much on both on all the value chain of robotics. So the actual manufacturer should be able to find the right partner that helps them build along the security in the pathway towards the market, and this spans towards the system integrator and also, of course, towards the end user. Upon non-industrial deployments, this is, of course, more of a responsibility of a manufacturer as far as you remove the components of the value chain. However, as we are seeing, and we were discussing this pretty much yesterday as well, it is always a shared responsibility of, maintaining and adopting the right cybersecurity position of all the actors in the value chain, including the security partners or the defenders that may act upon the security value chain.
Okay, so yeah, the mute button, always the same thing. So in the case of Aldekin, have you been investigating some of the systems there as well, Andika? And maybe you can also ask a bit more towards Ibai on how their relation, for instance, was with their customer in the end, and so how it's basically maybe also improved their situation.
Now, security of collaborative robots of use case 3, for example, it's been widely investigated by other groups earlier than us. For example, in 2017, that existed previous instances of vulnerabilities and previous exploits that could lead effectively to safety adverse effects, for example. Now, this is something that will be expanding towards other domains, and we believe it is a must to speak openly on this as soon as possible, to be able to spread the word and be able to raise the awareness of all the agents in the value chain. Effectively, there's no way we understand manufacturers are gonna have the incentive towards building security if the end user is not aware of the problems that could be happening out there. I love to launch a question to Ibai at this point, and is upon the fact that we have witnessed a lot of secrecy around these robot cybersecurity incidents. So on the one hand, Ibai, why do you think is that? And on the second hand, do you think it benefits that we speak openly about incidents like this one? Of course, maintaining the confidentiality of the customers involved.
Yeah, I think it's positive, because I think the main issue or problem of cybersecurity in robotics is that I think the people think that a robot can't be infected. It's just a thing of computers and laptops and these things. They don't think that the machines can be infected. And answering the question that how was the infected the robot burning through Ethernet cache, we thought that it was through the USB drive, that someone went with his USB drive to copy a new version of the programs and change that maybe he uses at home to do something, because the robot was not connected to the IT network, to the network of the company. So I think it's positive to share the danger of which is the situation, because people, as I said, people think that it's not a problem of robots, at least our customers. And we have customers from very small SMEs to very, very big companies. And the thing, the cybersecurity, it's not and when we offer your services, a lot of people look at us like, what are you offering? It's a robot. It has nothing to do. So I think it's a good thing to share, just to realize that it can't happen. It can't happen to everyone. It's like at home. We can't have an infected computer. We can't have an infected robot or machine.
Go ahead.
That's interesting when it comes to these incidents that are not at least widely in the media. But Ibai, do you believe these companies that you have witnessed in the past with hacked robots have any common traits or any common, let's say, attributes that could make them target for cyber attackers, or could be just, making them on the profitable side of an attack?
Two of them were or are big companies, but the other one, it's an SME of 50 people or 75. I mean, the other two ones, the hospital and the other company are big hospital. It's a very big hospital, and the other one, it's a very big company. So I don't know. These two are big entities, but the other one, it's like a common SME of any town or any city. I mean, it has nothing special.
I believe that attackers take also the path of least resistance sometimes. No, we were sharing this with the speakers from Leven today, that you have to take the attacker's mindset sometimes to defend actually the systems that are your target. Sometimes systems that are assumed to work in isolation, such as industrial robots in this case, are no longer holding to that paradigm, and Industry 4 is changing the way that these systems are interconnected right now. This cybersecurity agnostic position of manufacturers does not hold any longer, and you have to work assuming that there's gonna be attempts of trying to get in, and that the attackers will try to find the least or the most valuable and protected assets in the, let's say, setup that you will be building. At least that's my experience, and I believe that the most, or the, let's say, the common trait sometimes is the path of least resistance towards this attacker.
I don't know, because we don't have a continued collaboration with these two entities, or these entities. So I don't know. And it's cybersecurity in robotics. It's a very, I don't know, very new thing, and they didn't share too much information with us. I think it's a problem too, because if you want to solve something, I think that you should share. Answering the question, we are not sure that it was a pen drive. We think that it was a pen drive because we see changes in the program, in the main program, in the data, and we see changes, and we thought that making assumptions. The first network card was born this date, and the program was changed in this date. So I think if they have another kind of problem, they can share with you a lot of everything. But with this kind of problems, at least in our little experience, it's like, I don't know if they are ashamed or what, but they didn't share too much with us. So I don't know.
I think that's quite normal. So to put it a bit into perspective, and maybe Leonard and Mikael, if you're back, I can't see you, but please join in here to open up maybe the conversation a bit further. So Leonard, Benedict, and you were asking about basically threat models here. I think you've seen a couple now. Any interaction, any reaction from your side?
Yeah, I think it's fascinating that these robots actually get compromised and that they even cause harm to people. It's the first time I hear about such a
very big. It was a very big harm and very big important issue. A very important issue in the company.
Yeah. And then maybe also to add to the path of least resistance. I think that's really the case that if I was asked to compromise a system, I would go for the path of least resistance. But I think in many cases, people always think that they don't get hacked because they don't have anything interesting or because they won't be targeted specifically. But with the way that these systems work, you don't have to be targeted specifically. We've seen that with these big ransomware attacks where someone finds a vulnerability and then just tries to compromise as many systems as they can find on the internet. So you don't have to be targeted specifically to be the victim of such an attack. So if someone takes a popular robot, figures out how it works, comes up with an attack, there's no reason he wouldn't try to attack all of these robots instead of just one, basically.
Yeah. So and I think the same is there in terms of the perspective from shall we or shall we not share. I think in many and most cases today still we see that there's especially also in this type of cases companies don't like to talk about it because they are probably afraid of being held responsible for it, which I guess in any case it will happen. Yesterday we had the conversation also with the German Institute for Insurance, and that has been investigating also the liabilities in this case. So if we take those two issues and bring them further along to some of the manufacturers, I think it becomes quite clear why there's something more that needs to be done in this space. I don't see that. Mikael probably hasn't been able to join in anymore. So good that we had at least a couple of discussion with him. Andika, any afterthoughts from you on these type of examples? I mean, how would it be feasible according to you, and taking it maybe a step further towards the future? Let's say that we can be relatively sure from where we stand now that these types of cases will happen more often, will cause much more harm. I think that's probably an assumption that we can make in this forum. So given this, what are the better steps to take from where we are now in trying to secure it? I think it's been clear that it really is not no one single entity that can deliver a solution. You made also the point that you have to have reliable partners. But taking it step by step, and let's say that 2021 we would be able to give some real concrete guidance. What would be the first guidance that we need to give them?
Well, I think that we have all to reckon that cybersecurity has got an intrinsic value. It's not the value of the loss itself, but it's the value of something intrinsic that needs to be built upon several levels of the value chain. So it's always easier for somebody to have the quantification of something into, economic terms, but we all have to reckon that cybersecurity is a must, and we will have to reckon its intrinsic value if we don't want to be, let's say, suffering the adverse consequences. So this is something that needs to be worked upon different levels and different levels of the value chain, of course, and this has to be change of mindset that will be perhaps triggered by, let's say, consequences of events, or in my opinion, it should be triggered by a joint effort of all the actors of the value chain. So I would love as well to extend this to Ibai and their experience from a perspective of system integration, or system integrator, sorry. But still, I believe that the actors of the value chain do not speak the same languages when it comes to cybersecurity. So the manufacturers have some concern, the actual system integrator has very different ones, and the end user has got very different ones. So we need to find a common language throughout the way.
Yeah. I think that's an important issue, because in the previous presentation, I didn't almost understand anything. So, but yeah, I think it's a very important thing. But I think in the first step, it's just to share, not the problems, but to share that hacking robots, it's a real thing. It's an actual thing. It's not something of the future or something very improbably that the Leonard said. When you don't need to have something very important to be hacked. So I think it's the main work to do, or the first step to do, is to concern everyone that it can happen. And after that, we can't, if we realize and we accept the problem, we can't give the steps to solve it.
So Ibai, one before last question to you, and again, thanks for sharing your experiences here. If you would, as a system integrator now, in all of your next assignments, if you would add maybe 5 to 10% budget increase for adding cybersecurity to your projects, how do you think your potential customers will react and your customers will react?
I don't think the problem is the percent of the budget in those terms. If we are talking about 5% of 10%, I don't think it's a problem. The problem, or it could happen that they think it's a waste. It's not about the how much is it, but it's like 30,000 or euros for what? No, I don't want that. In the most cases, in the ones that they are concerned about the cybersecurity, I don't think it's a problem to increase this in those terms.
Okay, so I think that's valuable information in any case, because this way you can at least understand and try to find ways to tackle that issue, because I think there's plenty of routes out there that we can be convincing enough to showcase what it could mean for them, and what a potential risk impact it would cause if they don't take the necessary preventative measures in this case. Okay, and then I'd say final question to all of you for New Year's resolution. In this case, what do you think would we need to do as an industry, both security, robotics systems integrators, as a real concrete step towards the market of both robot users already out there? Yesterday, I gave an impression of what we've been doing within Trinity over the last year in terms of just by raising the level of awareness, getting the attraction of the different partners, and starting to think on how they can further improve, in any case, their use cases. And we see that those small steps actually lead to some form of a maturity improvement, but also of an improvement of the cybersecurity case in total. So each and every one of you, what would you say is a good resolution to take, and how can we further take this to a next step in 2021? Andika, you go first.
So I would say it's a matter of taking 2021 as the year of building the right incentives, right, towards all the actors that are involved. It's a matter of building the right incentives towards robot manufacturers that are manufacturing the products that will be used tomorrow in industry, but also in our houses and in many other places such as hospitals. It's a matter of building, recognizing the intrinsic value for them, which as of now have little incentives in many cases. It's a matter of having the right incentives for system integrators as well that are building upon industrial or not use cases. But it's also a matter of finding the right incentives towards the end users. So I would say that one way of finding these incentives in the overall landscape is to make them aware of the consequences of these particular incidents to their particular businesses. So it's a matter of a shared responsibility, we know, but upon an incident such as the one that Ibai described before, the very first thing somebody would do is to call the insurance, and then the insurance would kick off investigations, and the investigations will drop into each particular or each one of the particular stakeholders of the value chain. So let's say the value of being protected is something intrinsic that could help your business have, future trouble or future potential liabilities in relation to what could your technology be causing, or what your use of technology be causing to your actual business.
Thanks. Leonard, I think you by now know almost everything about incentives, and definitely incentive schemes of responsible disclosure as well. I think what the case that you showed from the Tesla that you stole, my Tesla, that specific case, I think, also indicated that if you take big brands, worldwide known brands with lots of media impact, that it also helps. So shall we try and find a robot which has a global impact as well, in the same way as the autonomous driving?
I think that would actually help. So I'm under the impression that maybe there's not enough awareness about the security issues in these robots, and that maybe even the people using these robots don't realize what can go wrong. And this is something we also saw with automotive products a few years ago. So there was this big hack by Charlie Miller and Chris Valacek, where they hacked a Jeep car, and then with the journalist inside of the vehicle, they ran the vehicle in a ditch. And that, for some reason, created this big shockwave to the automotive industry, where they suddenly started realizing that they need to invest more money in security, even though that a similar kind of attack was done 2 years before in a more academic context, where there was only a paper and there wasn't this cool video about how the attack worked, and it didn't raise enough media attention. And I think having these videos that go with the attack and that show how things can really go wrong in practice helps with waking up people, basically, and showing them that they should improve on these things.
Of course, you have to have good actors to do that. That's
yes, of course.
really good.
Thank you, Ulrich.
Okay, Ibai, some final words from your end. In the next, let's say that you meet your next customers, what are your recommendations to them?
To the customers, I will say that that we need, and to, as I said before, to tell them that it's a real problem, okay? And with the IoT coming, will be a bigger problem. So I think that we need to generate in the concern of cybersecurity in robotics, not only for the personal computers and laptops and these things, also in the machines, in the robots. That's what I see.
And we'll also make some work on helping US systems integrators getting a much more understandable way of
yeah, for sure. Yeah.
And also working towards improving, let's say, the way that we communicate in order to be able to do that. So thanks to the three of you again for sharing your views. Let's switch gears practically and physically. We already talked a bit about cars and autonomous things. Hello, Andres. Good morning to you, and welcome on this side of the pond.
Good afternoon in Europe, and good morning in America.
So how are you keeping up with the snow over there?
Well, yes, we did have quite a bit of snow yesterday, and so I had to do some cleaning. It's always a good way to exercise.
Absolutely. So I'd say send some over here, because we're anxious to get some white Christmas, but with 12 degrees Celsius out there, it's not going to happen anywhere near soon. Anyways, you've seen, I think, a couple of interesting perspectives and viewpoints, and well, we were obviously very excited that our partner Mass Robotics has invited you in here to talk about some of the work that you have been doing within MITRE. So maybe it could help in explaining just in a couple of words who MITRE is here as well. We from Cybersecurity Land know MITRE very well because we work together on many different aspects. But we haven't worked on the adversarial scenarios with MITRE. So please enlighten us with some of the works that you've been doing. Thanks.
Thank you, Ulrich. So certainly, MITRE it's an organization in the United States, and our general mission is to solve problems for a safer world. And in particular, I lead two teams of researchers that are solving problems in the area of trustworthy autonomy. And one of these projects is related to autonomous vehicles. So that's in fact what I plan to talk about today. And please do let me know if you can see my presentation.
Yeah, sorry, I was looking for the mute button. Yes, I can. We can see basically your presentation from the perspective of the presenter. So big slide on the left and then the smallest slide on the right.
Mm-hmm.
That's fine. So if it doesn't work out, I still have your a backup here. But I think in the PDF that I have, probably it's going to be less.
Right. So let's take another shot. let me know if you do see my presentation right now.
Yes, yes. Now it's full screen.
Excellent. So certainly, so again, thank you, Ulrich. And so what I'm going to talk about today is related to, as I mentioned, one of the two projects that I lead related to autonomous vehicles. And I really appreciate the opportunity to talk in this venue because it's really important for us as a community to start thinking about how to evaluate the assurance of autonomous vehicles, particularly in adversarial scenarios. And what I'm going to talk about today is focused on the challenges that we have encountered while performing research in this area. And I hope that actually the points that I make contribute to interesting discussions in the panel afterwards. Now, one of the things that I had to recognize is that autonomous vehicles are very complex systems, and actually many of the ways in which you can attack these systems includes many of the ways that have been discussed in this conference already. They include communication attacks or attacks via software flaws. And in general, when we think about the security of autonomous vehicles, we certainly have to think in a holistic manner. But what I'm going to talk about today is focus on one particular emerging threat and one that actually we're addressing at MITRE, and that is related to the fact that autonomous vehicles are going to be driving on public roads and being exposed to an adversary that has the ability to manipulate the environment in new ways in order to bias the decisions of an autonomous vehicle. So a concrete picture that we have to keep in mind is one, for instance, in which an autonomous vehicle approaches an intersection and this stop sign has been manipulated by an adversary so that the stop sign actually does not get recognized as a stop sign. Now, depending on how the decision-making is implemented in this vehicle, it's possible that that's sufficient for the vehicle not to stop at the intersection like it's supposed to. And as a consequence, we'll see a scenario where we get an accident like this, which is catastrophic. So the noble thing here is that an adversary now will be able to influence the decisions of these types of systems without gaining direct access to the vehicle and basically through manipulating the environment. Now, attacks or adversarial machine learning in general has gained a lot of attention over the last few years. And part of it has been through attacks known in the computer vision world. However, the type of attack that I show you, it can be more general, right? So for instance, in this particular video, we can see that other researchers have already explored the idea of actually not only influencing the decisions through attacking camera-based object detectors, but also LiDAR-based object detectors. So what we see here in this particular video is 3D mesh that can be placed on the top of a vehicle. And as a consequence, the autonomous vehicle may fail to recognize this object as a vehicle altogether. So now we can imagine that in a video or in a scenario similar to what we saw in the previous video, the fact that the autonomous vehicle recognizes a different set of objects in the world, and perhaps this object is recognized as a static object, may actually induce unsafe situations. So one of the main points I want to make today is that while these two videos show like a problem that we have to be concerned about when full autonomy enters the picture, what I argue is that we had to deal with this problem today because automatic driving systems have already been deployed in the world. And in fact, increasingly, vehicles include features with a degree of autonomy that needs to be evaluated with rigorous approaches to understand what are the safety implications. For example, organizations like the Consumer Reports in the United States that have traditionally looked into evaluating products and particular vehicles from the standpoint of reliability, of best value, comfort, etc., have already started to look into, for instance, the new features that we have in vehicles such as the Tesla. So what you see in this very brief video is the outcomes of our review of Tesla's autopilot that show that as of the review of this video, the performance of the autopilot was far from consistent. So when you can see this vehicle approaching an intersection with a stop sign that is supposed to be recognized, it doesn't. So the driver has to stop. In other cases, you have the vehicle performing, for instance, slamming on the brakes when presented with other kinds of signs, or stopping in an intersection with a green light. And this is because the vehicle expects certain interaction from the driver, and when it doesn't, you get that type of behavior. So as this review explains, at best, that's just confusing for the driver, but at worst, actually, it presents a risk not just for the driver or the passengers of that vehicle, but also for other vehicles around that, for instance, may not understand how to react to this new behavior for autonomous vehicles. Now, beyond the fact that we need to understand this type of assessments better. So we don't only need to know that sometimes it works and sometimes it doesn't. We need to really precisely understand what are the conditions under which these types of systems may fail and may produce unsafe behavior. But institutions like, for instance, Consumer Reports may not be in the best position to actually address a new type of challenge, which is what happens when these vehicles are presented with adversarial objects in the environment that may induce behavior that is unsafe. So that's why I think we had to start tackling that problem today. And perhaps one way to start tackling the problem is to recognize that the motion planning problem can be divided in multiple layers. And I know this division can change slightly depending on the particular decision-making platform. But the main point I want to make is that this middle layer, where the high-level actions are determined to accomplish a mission and subject to what objects are on the road and what are the rules of the particular road, let's say, are particularly susceptible to perception attacks. So the kinds of attacks that I alluded to at the beginning of the presentation. In particular, when we take a look at the inputs and outputs of this middle layer, we can see that the behavioral planner is going to try to understand what to do based on the rules of the road and objects that are perceived around the vehicle. And that perception of where the vehicle is, where other actors are, and what other actors exist in the scene, it's coming from data that has been shown susceptible to attacks, including GNSS attacks, including attacks to camera-based object detectors, and also attacks to LiDAR-based object detectors. So if the types of conclusions that are made are very much dependent on these inputs, then we can see that the problem of securing it's something we had to tackle today. Now, it's important to understand that we had to start integrating defenses for this type of problem. But even if we had already some defense approaches available today, still a difficult problem to understand which ones are effective in context. Part of it is related to the fact that defenses can come in a variety of ways. For example, they can certainly apply at the algorithmic level. So you can imagine that you can implement object detectors that are trained to determine or to filter bogus objects. Or you can combine additional information, not just the images and the outputs of an object detector, but you instead you can combine knowledge that you know about the geometry of objects or potentially dynamics that should hold in the world to get more robust decisions. And also, you can imagine that another type of defense approach has the idea of basically combining multiple sensors to try to make decisions more robust. For example, I don't know if you can tell, but there's in this image there's a person in the back that is hard to see via the camera, but it can potentially be seen via a LiDAR. But all of these approaches, if we implement defenses around those approaches, we have to understand all the caveats. For example, the specific attack may have multiple variations. In fact, you may choose to perturb a stop sign using a sort of target class as a person. So for instance, you can create perturbations so the stop sign looks like a person, but it could look like a vehicle, it could look like a basketball, it could look like a variety of other objects. And also the parameters of the perturbation, in other words, how much noise you add to the stop sign matter a lot. Not all perturbations are going to be equally effective under a variety of lighting conditions, distance, angles, etc. And when we think about how to fuse information, it is not always easy to understand how to encode all our assumptions about the various types of information that we're fusing. And at the same time, we had to recognize that multiple sensors can be attacked in a coordinated manner. So simply adding sensor fusion to the picture does not necessarily imply that we have a more robust decision-making approach, because we had to reason about the possibility of multiple sensors being attacked. So at MITRE, we are working on this problem. We want to understand how to evaluate the extent to which a system is adequately protected. And our take is that in order to make that type of assessment, it's not sufficient to simply list the number of attacks and defenses. It's important to create probabilistic models that actually take into account the specific valid behavior you want to protect, the specific ways in which you're integrating defenses in your security system, and the specific assumptions that you're making about the threats that you're trying to mitigate. Only when you have models that capture this concretely, your conclusions are going to be valid. Now, the problem as a whole, we think of two aspects of it. One of them is that you have to specify your problem, put together all the assumptions that you have here. But ultimately, these models had to be tools that allowed you to estimate what we care about, which is what's the probability that you're going to end up in an unsafe situation. And that second aspect, it's about turning the models into inference questions that you can estimate. And also along the way, you have to be able to simulate a large number of experiences from which you can perhaps make such estimates. Now, just to give you a concrete idea of the types of models that we're building and what are the inputs of that, those models, our reasoning is that you have to model assurance by understanding uncertainty, and you basically can start raising uncertainty as assumptions that you have about the world do not seem to hold based on the observations that the vehicle perceives. Concretely, you can combine information that you get from object detectors and information that you know about maps and position of signs on a particular area to understand that there are inconsistencies. So for instance, you might know where signs are supposed to be placed, but when you make that type of correlation, you have to understand that that has to be probabilistic, because sometimes stop signs are not going to be available or not going to be visible. You know, you can imagine they can be blocked by a delivery truck, or in some cases you're going to have stop signs that are perfectly legal because they're placed in case of constructions or perhaps at a time of school crossing. Now, in addition to that, you have the ability to understand how sensors, multiple sensors, are supposed to be correlated to see if observations in the world later on exhibit deviation on those observations, on those correlations. Concretely, this image has been processed via two object detectors, FASTER RCNN and YOLO. And as we can see, the outcomes of those two object detectors are not the same, but they're correlated. And that correlation can be made a little precise so that you understand how these are supposed to be correlated on a variety of conditions. Similarly, you can understand the performance of various object detectors across multiple frames. So if you think about a stream of observations, you can see how they correlate over time. For instance, you can imagine that what you expect to see is that as soon as you detect an object, that object proceeds on the scene with certain probability. And when you see the type of fluctuation where the stop sign, or in this case, is detected in some frames, but is not detected in other frames in a manner that is inconsistent with your prior assumptions, then you can start raising uncertainty, and as a consequence, lowering your assurance. So concretely, what we want to enable is it's a framework, a formal framework to allow those who are designing decision-making platforms to really start answering or reasoning about the question of how difficult it is for an adversary to generate adversarial objects and present them to an autonomous vehicle, so that they can bypass a collection of assurance mechanisms, and as a consequence, result in invalid behavior. If the answer to that question is that it's difficult for an adversary to be able to do that, then that's when you can conclude that there's high assurance on your decision-making platform. And of course, that's always going to be subject to the various assumptions that you make about your threats and how your assurance mechanisms are integrated in your system. part of this research has been increasingly possible because we're now at the position where we can use powerful simulation tools like Carla, which is an autonomous vehicle simulator that allows us to essentially simulate physical attacks. So what we see here, it's a video where we see a stop sign, sort of like the one we had at the beginning of the presentation, where we have this stop sign as a physical attack, because rather than taking every frame of this video and adding noise to the image digitally, what we have is the ability to design the perturbation, inject that perturbation in the world. In other words, place that sticker, if you will, on a stop sign and render it in the virtual world that we're experimenting in a variety of conditions: weather conditions, light conditions, with a variety of traffic conditions, at various speeds of the vehicle, various angles, etc. So that type of thing is possible today, and that's very important. And simulation tools like Carla also allow us to inform our priors. So a few slides ago, I mentioned that part of it has to do with understanding multiple correlations of multiple sensors. And so you had to be able to inform those priors. And so here, for instance, I show a video of the types of things that you can experiment with, which include understanding the performance of, in this case, faster RCNN on a variety of conditions. Here you have a rainy condition and a vehicle approaching an intersection, a specific speed. And then you can understand how a different object detector performs on similar situations. So here you have a different object detector, and as you can see, in fact, this object detector happens to detect the stop sign at a farther distance, and in general, it's in this particular video we see that it detects a stop sign with higher accuracy than the other object detector. So when you do that systematically on a variety of conditions, then you can inform priors that then you can turn into probabilistic models. And our preliminary research has shown that with relatively simple models, you can start reasoning about the extent to which your environment has been manipulated. So, for example, these are two scenarios. One where you have a normal situation where the stop sign in this case has not been manipulated, and here similar situation, but now where the stop sign has been manipulated. And via the approach that we're enabling, we can develop models that basically allow us to ask the question: are the observations that I'm gathering consistent with prior assumptions that I made? And what we have is when we go into this intersection, because this particular video has a stop sign that has been manipulated, then the correlations between the two object detectors and the correlations of detections over time do not match our prior assumptions. What we can conclude is that this situation is uncertain. So in other words, the uncertainty goes up, and therefore your assurance on the decision should be lower. Now, we had to also take into account that the assurance of decision making is it's also about what do you do with understanding the uncertainty of the situation. So for example, if a decision-making platform takes this information and then transitions to a safer mode, perhaps asking assistance from the driver or pulling over, that is potentially better than approaching the intersection normally, as if nothing else or is going on. No, now at this point, I just gave you a taste of the research that we're pursuing at MITRE, and there's certainly many challenges that we still need to address. In particular, the probabilistic models that we're developing have to be maintained, and many more have to be developed, and we had to understand how difficult it is for people to start developing these models, and how difficult it would be to maintain them. In addition to that, a lot of the conclusions that I show you in this video, in this presentation, include videos from simulation and analysis that come from simulated attacks. But we had to understand how to translate the learnings of simulation to real autonomous vehicles. And in fact, the closing the simulation to real gap is going beyond using real autonomous vehicles, but it also has to do with using real autonomous decision-making platforms like the ones that are being deployed right now. So this year, actually, we're already working with a team at MITRE that has autonomous vehicles. So we're going to be transitioning our research into that type of assessment with real vehicles. But we still need to get availability of decision-making platforms that are sophisticated and that people are thinking of moving it to the next level of deployment, and unfortunately that's always a challenge to get that type of decision-making platform. Similarly, to really understand the applications of our approach, we had to evaluate the extent to which the inference tasks are computationally efficient. So perhaps it was not obvious, but there are two potential use cases for what we're looking at. So you can think about a platform assessments that are pre-deployment. So as individuals or institutions are developing decision-making platforms, they can understand how well their decision-making platforms withstand attacks like the ones I illustrated, and as a consequence improve their decision-making platforms. But you can also imagine that a version of this framework can be used to create monitors that, after the vehicle is deployed, they continue to monitor the observations that are feeding that are being fed to decisions, to really assess the probability that an attack is taking place. And for that, we need certainly inferences that are highly efficient. So the main point I want to make here is that we really need to start thinking about how to evaluate the assurance of automatic driving systems. We had to start addressing that problem today, and we are already doing some work at MITRE in that regard. And we hope that very soon we make a framework available for the community to start basically developing more secure and safer autonomous decision-making platforms. So with that, if anybody wants to follow up, you can send me an email. Or at MITRE, we're really looking forward to engage with the community at large, because we believe this is an important problem that contributes to a safer world. And thank you very much for your attention.
Thank you very much, Andres. Very interesting work indeed, and I think highly relevant for all of the visual inspection capabilities that we see popping up in many of the robotic systems today. I was in your last slides, on the conclusion slides, you have this software tool with ROS interfaces and efficient algorithms. Can you tell a little bit more about that? It says in progress, because
right.
I think that's probably something that will interest at least this community.
Absolutely. So one of so let me perhaps go back one slide, which is so we can certainly do some of the work in simulation, and Carla, which is one of the simulation platforms that we've been using, allows you to interact with autonomous vehicles through, let's say, Python interfaces. Mm-hmm. But what we want is to be able to use real autonomous vehicles, and also platforms that, or decision-making platforms that are developed not just for Carla, but actually to interact with real vehicles. Mm-hmm. And so for that, we have understood that we really need to have that layer of communication that allows us to get observations from Carla or from a real vehicle via ROS, and also tap into the decision making that is being sent by the decision making platforms, also through tapping to that middle layer. And so for that reason, we're investing time on making sure that our software tool can basically tap into a system that already uses ROS to collect the information from the sensors, and also to send actions for the autonomous vehicle, either simulated or real, through a ROS interface. So we're planning to do that. We're working on that this year.
Okay, so do ensure that also, of course, interacts with the security components that Mikael was talking about earlier.
Absolutely.
ROS 2. Great. Well, thank you very much for this. We'll pick up on the rest of some of the work afterwards, because we're running a little bit behind on schedule now.
Absolutely.
There's some time that we can catch up during the panel discussion, but I would like to hand over to somebody that's probably not too far away from you, also in the US. Hi, Eric. How are you doing?
Fine, thanks. How are you? Yeah, I'm in snowy Boston.
Yeah, we learned about the snow already yesterday and today, so it's good to see that you're still alive and well, and not too much snowed under.
Yeah, well, no, the worst thing is, I'll tell you, so you usually get snow days when it comes this much snow, but during a pandemic and you're working remotely, it explicit you might not get a snow day because you're already working remotely, so you can't come into the office.
Absolutely.
So there was no snow day benefit, only shoveling.
See, yeah, that's done in this case. Yeah, a bad thing. Anyways, I think it's better to be snowed under with snow today than with work in this last day before the holiday season starts picking up. And so actually, you're going to be our last speaker of the day and of this conference. Very happy to have you here. When we were talking about robots, Of course, the impact of robots together with artificial intelligence is increasingly also speeding up. Also in the terms of in the world of cybersecurity, we have seen over the last 5-6 years machine learning turning into behavioral analytics, turning into sort of general purpose type of AI, I would even call it. But the effect of it is clearly there. It really has shown already a lot of benefits and is showing still a lot of potential benefit, but also from not only from the defense side, but also from the attacker side. And so I think one of the things that we have to start learning also from the previous talk is how AI can actually be starting to be used against us when we are applying it for security purposes. So I can also quickly tell that we're going to start within our activities early on next year with some projects in that space. And I'm definitely looking forward to sharing some of your experiences and expertise. So take the floor and let us know what you're working on.
Oh, thank you. So start sharing my screen here. Okay. So hopefully everyone sees my presentation and not my presentation mode.
Yes, we can.
Okay, excellent. Okay, so I'm going to talk quite broadly about adversarial AI, but then I will dive into some specifics on the research that we've been doing. So my name is Eric Hemberg, and I'm a research scientist in the Alpha Group at MIT CSfR. So really the agenda is I'm going to broadly try to put AI into into kind of existing cybersecurity, so we're on the same page there. And then we're going to focus on using min-max optimization to improve the robustness of AI. So we're going to have examples regarding malware detection, a framework where we can look at how we could use it for improving network security. And then also we're going to look at generative adversarial networks to improve their training. So to start with, we'll just look at cybersecurity very broadly. So the point there is to say we want to minimize the points, that is the attack surface where an adversary can penetrate. And in order to do that, we need to identify the components in our system. So there would be hardware which has CPUs and so forth, and there will be software with operating systems and different applications. And there, in those, we need to find out and distinguish the different indicators of exposure and compromise that might be there. Then we need to also consider the impact of an attack on our system. Because the impact could be, for example, regarding confidentiality, that is when someone leaks data, which can be harmful. Then there's also, for example, someone leaks a lot of credit card numbers. Then there's integrity, when you've seen someone's been in the system, but you haven't seen any data being leaked, but the records could be modified. So you're not sure if someone changed the data that existed in the system. And then finally, we also have the accessibility, where someone can deny a service of a system. And that could be, for example, if I have a website, someone does a denial of service attack, so no one legitimate can access my website. But then you get that transition towards more of the physical domain. For example, if you have a ransomware attack on a hospital and the hospital can't access its IT system, there it can have major impact on the service that hospital is providing, which is patient care. So the impact can then be in the financial, the physical, mental impact, and reputational impact. Another thing to consider in cybersecurity is what is the goals of the adversary? Like, what's the strategic goal and what the adversary wants to be achieving? What is the sequence of tactics that the adversary would use in order to achieve that goal? And then for achieving that tactics, what are possible techniques that are using? So I'm showing examples here, just a brief one, because we're going to touch on the tactics of defense evasion, discovery, and lateral movement. And there, MITRE has an extremely good research called the MITRE attack matrix that divides up these different tactics for for the cyber kill chain, where you can see tactics and you can see techniques related to those tactics, and you can find different procedures and groups that could be using them, and you can even link further down into specific vulnerabilities. But that's amazing good research, and for a completely different talk. Now we're going to focus on the defense evasion and discovering lateral movement here. So really, the first example we're going to look at as a system we named Sleipnir, which is adversarial deep learning for robust detection of binary encoded malware. So what is that? Well, machine learning models, they're vulnerable to what is called adversarial examples. So it's basically a small change. And we've seen many examples of vision already where you make change. But when you do it for malware, there's some things you need to consider. So the first thing we need to ask ourselves if we can have a detector. So what we were wondering was saying like, well, if we have a malware detector, can we improve that? So we harden it by training it on adversarially learned data. So we're augmenting the training data for our malware detector with data that we created using adversarial examples. So the trick with malware is that in order for you to have successful malware, it still needs to be functioning. So, and everyone knows that it's hard to write code without trying to avoid detection. Compilation's hard, period. So you need to be careful with what you're perturbing when you're trying to perturb software. So we looked at what were these portable executable files. So these are files that are executed on a Windows machine, and we parse them with the leaf parser to extract imports. So what we said is that, well, we can perturb, or in our case here, add imports to the executable, and that will not alter the functionality of the program, because if I just add an import I'm not using, the code will still function. So for example, the example here I'm showing on the right, left there is a malicious code. So it says import bad library, and then it has a bad function that calls the do evil function in the bad library. So if we have a detector that is based on identifying uses of bad library, it would detect, oh, it uses the bad library. But an adversarial perturbation of this binary could be that you just add an import to some library, and that could fool your detector to believe that the code is benign, even though the bad function still does evil. So that's an explicit example of what we were looking at with adversarial examples in malware. So if we just take a step back to see, well, what are we talking in a more general sense in machine learning here? So really, we're basically having our model, which takes some input data X, and then that model is some function that takes the X and some parameters theta and gives output Y. So also then what we need to consider for the cybersecurity is that the ML model is often an additional component in our system. For example, a software application. So we're adding another point of attack to our system. So we just need to consider it in the same way we did the other ones, but the peculiarities of how you can attack the AI model. So if we look at one way of just describing this cartoon of how do you attack AI models in a general sense. So here we're projecting some data points into a 2D space, and the points can either be X or O's, and then there's a discriminatory boundary drawn on the blue line. So as an adversary, I could try to do my adversarial perturbation, where I take the point that is marked in yellow, the X, and I add that epsilon perturbation that pushes it over the discriminatory line of the ML model. So it's going to believe that my X, classify my X as an O. The other way I could work is not perturb the data, but perturb the model itself. So I can try to modify the parameters that was used in the model, the theta. So we see the arrow going down, saying that maybe I can modify the discriminatory boundary of the ML model to then misclassify the X. Another point we want to be considering, so that's one general view you can take of it. Another thing you want to be concerned in when you're looking at attacks is saying like, well, what is the knowledge of the attacker on the ML model? Is it a black box attack where the attacker really only accesses the data and gets the label out? Or is it a white box attack where the attacker knows all your training data, all your training parameters, and the method that we're using? So these one, and then in between those variants would be a gray box attack. So these are different variants to think of when you look at AI security. So if we go, so another part then, when we talk about the attacks and then different mitigations that we care about, is that there can come attacks in different stages on when you're using your AI. Like in the data collection phase, someone could add noise to the data that you're going to use for training. Someone can add fake data to your collection, and someone can remove data that when you're trying to collect data. All of those will have impact on your model. When you're training, someone can perturb the data, the labels, and the parameters. And during inference, as in when you have your model deployed, someone again can try to perturb the parameters of the model that's being used to have it behave differently. They can try to evade the model, as we do in our binary malware example. They can also try to learn the model that you're using, so actually stealing the model, which you put all your hard work into creating. And they can also try to learn the training data set that was used and then steal the data that was used for that. So some mitigations that have various resource requirements would be that, well, you can use multiple models. You can try to detect the attack. That's a very general sentence. You can try to sanitize the input data to the model beforehand. And then what I will be focusing on here is to improve the robustness of the model with min-max optimization, as in adversarial training. So for example, augmenting the data set. So if we go back to the binary encoded malware example, which we call the Sleipnir framework, is that we have these malign portable executable files, and then we have benign portable executable files. And then we do this min-max optimization. So we have a neural network that's trying to distinguish the malign from the benign, and then we have an inner maximizer that tries to maximize the loss and use that to create these perturbations. And the trick here becomes is that since we're working in a discrete space where we're just allowed to add imports, that then how much we're going to be perturbing and what becomes a bit trickier. So that's what we're investigating here. And then the outer minimization is where we're trying to, the network's trying to detect as good as possible. So what we do here then is that we're creating all these adversarial examples that we're seeing in the top right. So that's what we can use for data augmentation. So I'm quickly going to go through some of the results that we had here, just to be more concrete. So what we see on the columns is what the adversary is doing during different attacks. So natural means that the adversary didn't do anything. Then the different names are different ways to do these adversarial perturbations. And 13th methods, that's a method taken from the literature that was previously done. This is the numbers show the evasion rate. That means how well the detector was avoided. So what we can see is that on the row where it says natural, we can see as soon as we're doing some adversarial perturbations, we get pretty good at avoiding the detector. We're getting up in the 99.7% of evasion. Then we're looking at, if we look at the rows, that's where we're saying like, but can we augment the data by using methods for creating our adversarial examples? So there we're seeing what happens to the evasion rate when we're augmenting our data, and then how well it goes against these different adversaries. So we can see that sometimes we can even get better, when we're augmenting the data, but there's also quite the big variation between what method you're using for augmenting data based on what the adversary is doing. So what the conclusion we can say is that the model hardening does improve the detection against adversarial examples, but there are differences within how you're doing that. So this was us looking at defense evasion. Now we're going to look at another step where you can, which is interesting, where you can use AI, which is deceptive defense with honeypots. So what we're considering here is that we have a network. So you have a network and you have devices on that network. what you want to avoid is have an adversary discover all the devices in your network and then move laterally between them. So one way of doing that would be to make larger networks. And before you'd need to buy more hardware and plug in more routers and networks. But now you can use something which is called a software-defined network. So that creates a virtual network. So by using that, you can create virtual views of the network for each device on the network. And the other thing you can do is that you can even put in honeypots. So that means that benign devices on your network should not try to go and find a honeypot, but a malign device that is scanning the network to discover things would get caught in one of these honeypots. So what this system has, as we were saying, it has the SDN controller, which controls the routing in the network. Then it has this network view generator, which generates the view for each device, what the network looks like. And then it has this deception server. So that is manipulating the traffic on the network and simulating these honeypots. So this one was used with the standard for SDN called the POX network. That was the POX SDN controller that has these deceptions added in. And then we ran this on Mininet, which is a simulator for SDN networks. And then our question is saying, like, so how do we find a good defensive configuration versus an attacker who would use Nmap, which is a scanning tool to find devices on the network? Well, we decided to look around at nature. So now we're going to take a small break here before we get back to that. So we looked at, well, what about this biological coevolution that can take us towards adversarial AI while looking at artificial coevolution? So since everyone is muted, you should write your answers to the next question in the chat. So I'm showing an image here and I can see, so you should write what you can see in this image. So I'm gonna monitor the chat here to see. So I see someone saying a bee. Yeah, we see a bee. And then we see a flower. So did anyone notice the yellow spider that's trying to eat the bee? So this is what we're seeing here. This is impressive adaptation where the spider has adapted to have the color of its favorite snacks. So by looking like a yellow flower, it can go and eat the bee. So this is an attacker adapting in order to catch its prey. Another defensive adaptation are these butterflies. So it's the viceroy and the monarch butterfly. So the viceroy is not a monarch butterfly, but it tries to look like one because some biologists claim that the monarch doesn't taste well to predators, so a defensive adaptation is to look like something that the predators don't like. So what we're looking at here then is to see, well, these biological arms races can provide adaptation. So is there some way for us in the methods to improve the robustness of the AI against attacks? So we're asking, can coevolution help to improve robustness in these adversarial settings that is not in nature? So what it can provide is multiple comparisons and diversity of solutions. If we have a similarity, we can help anticipate possible scenarios and also replay an arms race that could be happening. So we can capture the arms race, because what we know in serious security is that the adversary is going to attack you. And if he's thwarted, he's going to come back. So if we go back now to our network, we set up this concept. So we started out with this software-defined network use case. So this is kind of a general concept that you can use. So you need to think about, you have some threat environment, and then you have some objectives in that environment. Then the environment is what we end up calling the engagement environment, where you're measuring how the adversaries are doing, some simulation. And then you have the objectives that could be, you're looking at finding the best worst case the mean expected utility or some Pareto measure. And then you have the adversaries that, so we can create a population of attacker that we modify with some machine learning. So we need to know the attacker behaviors and the parameters we're passing into the learning algorithm. And then we can pick one individual from the attacker population and put it into an engagement environment. We can do the same thing for the defender. So we can look at the defender behaviors. We have the parameters for the learning algorithm, and we can pick defenders and put them into the engagement environment. So for taking it for the evolutionary analogy, you can call this a fitness evaluation. So you see how well does one attacker perform against a defender. So thinking about back of our network, the attacker is configurations for how to do a scan of a network. For the defender, it is how to configure your software-defined network. Then these are run through the Mininet, and we're getting measurements on how fast did the attacker detect all the devices in the network and how many honeypots did it hit. And the defender wants to make the attacker go as slow as possible and hit as many honeypots as possible, while the inverse for the attacker was the way we've set up. So this is how we can get the measurements and put up the evaluation of objectives. So here's how we can, one attacker can be tested against multiple defenders, and vice versa, we can try one defender against multiple attackers. So when we ran it in our SDN network, we got a few results. So one thing which is important is that first we're looking at how do we optimize our defense against a static attack. So we try to, in a sense, evolve and pick the good network configurations against static attack settings, that is Nmap scan settings. So that said that so the good solution there created subnets for DHCP leases that where real hosts are in different subnets, which is good. So that's intuitive because it means that don't put all your eggs in one basket. So make the attacker work for scanning to discover all the hosts when it scans subnets. When we doing it the other way, where we're optimizing the attacker, as in we have an evolving attack population against one static defense, as in one SDN network configuration, you can find that there's high risk, high reward tactic that comes out for the attacker. And then when we put them together is where it gets interesting, because if we co-evolve the attackers and the defenders, as in the attackers try to improve against the defense, then the defenders try to improve the attack, we can see that defender does significantly worse versus an evolving attacker. So that's where we really need to be careful about this, in the sense, the static assumption, as in just because we can create a really good defense against an attack does not mean that that's going to be a good attack in the future. So a good defense in the future. So we were trying to look at this in the way what the graph is showing briefly is saying, like, here we allow the attacker to improve more, and then the defender improved less. So we had kind of this asymmetric search that were allowed for the attackers and defenders. So we can see the attacker improves, and then the defender can improve, but then the attacker can improve even more. So this was kind of how we could use this coevolution in a network simulation. So then the last one thing I'm going to look at regarding AI and security is then for generative modeling. So now we're going to take a step back again, and we're going to reset our brains and say, like, well, this can be useful for defense evasion. So we want to think about that. So we have data that can be drawn from some distribution. And then we're wondering if we can learn a generative model that captures that distribution so we can generate new data samples. So one method of doing this is to use a generative adversarial network. So that also does some min-max optimization. So the generative adversarial network, it works the way that you have a generative and a discriminative model, and we have real data. And then we have some generator, which is a model that just takes noise in. That generates a fake image. So then we have a discriminator that gets an image or some data, which is going to say if that is fake or real. And then if the discriminator is correct, it gets some loss based on some loss function. Otherwise, the generator gets some loss based on the loss function. So the generator wants to fool the discriminator with fake data. And as it's doing that, it's getting better at, it should be getting better at generating having a distribution that looks like the real data distribution. So that can be used to create new data. But this is not an easy thing to do. So when you train GANs, you can say, well, we have a generator here. It's trained to create to generate images of digits between 0 and 9. But if we train it, we could end up having what's here. We see a mode collapse. So we managed to put a generator that was really good at generating the number 0, but then it failed on all the other modes. So you get these pathologies in GAN training where you can have a mode collapsing, you can have a discriminator collapsing, you have vanishing gradients where it's difficult to find some learning. So we can then look back and say, well, maybe we can combine the existing methods we had here in order to improve our GAN training, because we looked beforehand in the SDN networks, we had populations of solutions. And then in the malware, we had neural networks that were efficiently trained as discriminators. So what we do is then to create what we call spatial GAN coevolution. So we have a generator and discriminator, but we're creating a population of these. So that we have them on a toroidal grid. So we designate neighbors. So each cell has a neighborhood with north, south, east, west as neighbors. And then they get pooled in. So you have a population of generators and a population of discriminators. They get evaluated in all versus all. So we have a population, and then we select the best pair to replace that grid. And then we update the weights of the generator and discriminator, and this is our loop of how we're doing our training. So this allows us to improve the robustness of the generators and the discriminators. And then what we're also doing in order to get better generative capabilities is that we're creating all the generators from the neighborhood. So we have an ensemble or a mixture of generators. So this is what we created, a system we called LipSigner, which is distributed coevolution framework to train GANs with gradient-based optimizers. So we get fast convergence since we're doing gradient-based training, but we get the robustness from the coevolution since we don't have only one generator and one discriminator, but we can recover from collapses. And then we're also doing hyperparameter tuning with evolution. And since we have a mixture, we get diverse solutions. And finally, we can also get scalability since we have this spatial topology. We can distribute and compute these asynchronously because it can be computationally intense to do this. So just to briefly look at some results here, which is to say, well, why, Eric, it sounded very complicated, all the steps you had in this algorithm. Are they really useful? And it looks like it. So here we did an ablation study where we looked at MNIST data set for grid size, and FID is how good the generator ensemble is. And the baseline where we have all the features is the one that has the lowest FID score, which is what you aim for. And then when comparing it against other methods for evolutionary GAN training, normal GAN training, and different GAN architectures, and then looking at different loss functions in these populations of GANs, we can also see that we get an improvement. And here we ran everything for the same amount of compute time. So every method was allowed to compute for 9 hours. That's how we did it. So there we can see that. So we're able to improve the we can improve the robustness of this method. So from this whirlwind tour, we'll just do a whirlwind summary. So the key thing you probably want to look at are the first 3 links. So it has this resource that is newly generated. It's called the Adversarial Machine Learning Threat Matrix. That is developed by MITRE and other companies, which expands the MITRE attack matrix to try to consider machine learning threats. And that's a very new research. The other one is a link to where Microsoft is talking about how to secure artificial intelligence and machine learning. So it's from their engineering point of view on what you should be talking and thinking about. Then the final one is the trusted AI. So that's from a DARPA project where they're trying to create an adversarial robustness toolbox. So that brings in different methods you can test your AI against for robustness. The other links are for details of what I talked before, and then there were some organizations that provided funding as well. So yeah, and I think everyone is very happy to go to the panel, so I'll stop sharing and bring in the panel.
Thank you very much, Eric. There was a very in-depth, great overview on what you're doing in that space. And as you can see, it's evolving rapidly. But I think there's a lot of key learnings from this domain that we can apply also in the world of robotics. I think you applied it here definitely towards cybersecurity, which makes sense. But I think that many of those components in terms of how to create adversarial attacks, as we've also seen in Andre's presentation, it's something to really worry about when it's being applied towards robotics. And then on the other hand, the easiness, as we've also indicated already, how we can deal with robots overall. So maybe indeed, as you pointed out, can I ask your fellow panel members to start with Mina and Tom to add to the panel, Bernard and Andres? Great. Thanks for popping up. Here we go. So hello, all of you. Hi, Tom. Good to see you again.
Yeah, hello. Good, great to see you.
So it's hello, Mina. Nice to see you. How are you doing up north?
Quite good. We actually have some snow. I'm rather happy.
Okay, super. I see that you have my second most favorite robot sitting next to you again.
Yes, it's a source of envy for quite many.
Yeah, I've got mine. I've got my series here as well. So this one is still on the USB level, but it works whenever I need it. Anyways, so I think maybe a good thing to start with, Mina. You've listened in to some of the cybersecurity perspectives. You've seen a couple of our hacks. You're our guide when it comes to Trinity, and I explained to people yesterday what Trinity is all about. So maybe to kick off in this case the discussion and the conversation. How do you see the current developments and evolution of robotic systems overall, and then specifically in domain of let's say industrial practices, but also maybe to a wider extent, and how do you see basically the impact of all the things that you've seen this afternoon when it comes to cybersecurity, both in terms of the domestic robots from Leonard, and then of course the ways that they've applied this, the challenges in relation to the healthcare and the adversarial attacks, basically causing Ethernet cards to burn down. And then adding to this, of course, all of the things that we've just learned, adversarial attacks towards the autonomous vehicles, and basically how we should start thinking about these things and incorporating them again also within the programming likely of the robots. So any thoughts?
So quite a request. Thanks, Ulrich. This is my final day before the holidays, and it's 6:30 in Finland, but I'll try. So it was mentioned also by Endika that in the manufacturing field, in the robotics field, the systems are still assumed that they work alone, so they are standalone systems. And this actually goes for both robot systems and the manufacturing equipment. We still consider that these are safe because they are not connected to the IoT system or the platforms. In the same discussion, almost all of the SMEs which are considering collecting the data digitally from the factory floor, mainly from the robot cells or any of the automation equipment, they want to connect the systems directly to the IoT platform, and preferably getting the direct connection from the controller to the platform without having additional sensors in between. So meaning that we want to create the digital value chain from the factory floor to the customer systems, which in ideal world is quite nice. But none of the SMEs actually, the manufacturing SMEs, are discussing about the cybersecurity threats. They still consider that they are meaningless or small enough not to be noticed. But I think it was the Lennart who mentioned that they don't have to be the best companies because they are one link in the chain. They only have to be the weakest link in the chain. And this is not really realized at the moment among the small and medium-sized companies in the manufacturing field. So as the digital evolution goes, there will be quite a lot of data collection, direct connection to the World Wide Web, without perhaps realizing that there is the weakest link in the digital value chain, and they might be them. And this is something what I have also realized during the discussions with Ulrich and these seminars, that it's not paid enough attention. Actually, what Ibai showed on the presentation, they were quite good examples, but not many know them. And that's one thing, that we should have quite a lot of good examples, warning examples, very concrete, that this might happen. You might have a KUKA and it might be infected. And the only thing you know that it's burning the network cards. So that was my short comment.
Thanks. Tom, you've been listening in as well, and you're also very much on the robotics field. So what's your key learning and your key takeaway for this afternoon, and what will you be able to convey to your constituency and your stakeholders?
Yeah, so I think one of the things that I found interesting, and we had a little bit of a discussion yesterday and some more today, so I'll set it more in an example. So if you look at warehouse automation and AMRs on a warehouse floor, they are fully autonomous. And so this idea of, well, they're not connected to the network, they will roam the warehouse and perform their tasks in an autonomous manner. So we already heard and learned a little bit from Eric and Andres, but just because that system is autonomous, that doesn't mean there are ways that you can get in and corrupt its performance. And so if I'm optimizing a massive warehouse, like Amazon has hundreds of thousands of these shelf-moving robots, if I have the ability to get in and essentially interrupt their performance and change their behavior so that I can slow down that entire supply chain, I think people don't realize that that is something that will be a real threat. That will have, an adversary will have the ability by getting in and providing maybe data on the AI side, the model data. It's not going to be as robust as autonomous vehicles because people aren't looking. There's more attention being paid to autonomous vehicles on the roads, but that same ability to provide data that maybe the stop sign example that Andres gave, if I can come in and manipulate that data model so I don't know where the aisle ends and the intersections are and the forklifts are coming, I can disrupt an entire warehouse and the supply chain, especially when we're talking about a pandemic. I think that's an interesting thing that people are not looking at. And the other side of that is, even though they're fully autonomous, there's an upper level task manager for all of these warehouse robots. They come back and connect through the network to the outside world to get their next task. Yes, once that task is assigned, they will go to that section of the warehouse, pick that object, move it to the pack out area, whatever they do. That can all be autonomous, but they still have to get that task level through some network that may not be secure. And so I think there's numerous ways that these systems can be impacted. And I think that the vendors are still trying to figure out, and we had this discussion last year, I think it's still the case now, is they're still looking at early deployments. They're still trying to understand how they optimize their performance within the warehouse or the factory floor or wherever they are. And they're not thinking, okay, someone's going to alter the behavior from the outside. And so we've got to put incentives in for them to start looking at this problem, because I think it is a problem. We saw some examples today. I think it's only going to get worse as people realize that there are many more of these systems being deployed. So that's just a couple of things that I thought. I think great progress from last year, still a long way to go.
Bernard, you're the one that's been mostly involved in the security developments as well, and so some of the thoughts regarding AI must have already arrived also on your side. What do you think about some of the research work that you've been doing up to now, and how can we take it further, both in terms of the cybersecurity research in AI, implementing that on the robots? I think some of the examples that Eric was showing in relation to, for instance, the honeypots, the software defined networking configuration, and a couple of those are at least very valid as well to the robot environments and the way that they're being programmed. And also from Andre's side, I think the perspectives from the autonomous, the way the vision inspection systems are being used or can be manipulated. So any thoughts from your side?
Well, yes, of course, the thought has more than occurred that the more intelligence you try to get into a robot, the higher the risk that this might be a point of attack. And I totally agree that there is a lot to do in order to secure this, because the systems become more and more complex. They also become more and more intransparent, so we cannot really look at what the system is doing. And I think so what we've seen also from the presentation, what Andres recommended, that we have and basically constant self-checking of the systems, that they're actually functioning as to the specification, is exactly the point why we in security always say security has to start from the beginning of the development, because if you don't integrate functions like that from the start when you're working on the system, you will never be able to catch up to that. And so I think this is a very, very important work that they're doing, and of course will also be important for us in the future. And I think we will also need to have a larger system view on what can we do about this. So if we have security measures in AI, is this enough? Is it always sufficient? So like we have also been working on a cryptographic black box systems where you can actually log in a secure manner forensic data that cannot be manipulated, because you will have the situations that you want to look at what happened when something happened. And I think what we have also seen from Aldakin and Elias, that a manipulated robot actually hurt someone. This, I think, could be this one very critical turning point that we have always warned about over the last years, that this will happen. And my fear is that this will not be the last instance that we see of it. And I agree with Minna that this should be much more widely known that this actually starts to happen. And as a general comment, we have seen this in other areas, that attackers, they professionalize more and more, of course, that is a very old trend, but they're also becoming more and more interdisciplinary. So if you want to attack a chemical plant, and this actually happened, you have IT hacking guys teaming up with chemical experts. You will see the same stuff in robotics. I'm pretty sure about this. So we have to be aware that the attackers will be more than capable of doing, and they will not be script kids working or playing around. Of course, they will also do that, but the threat landscape will continue to increase. And I think Tom is absolutely right. There is still a long way to go. However, I'm positive that things are going into a good direction.
Is it really time, you think, to start thinking about autonomous factories today, and given also the perspective that we now have from the last year's activities in terms of seeing where manufacturing companies need to take precautions, need to be sure that they can provide preventative measures in terms of social distancing, in terms of keeping workers and employees working from home. So autonomous factories is getting much more a reality. Charlie and the chocolate factory. So can we imagine a secure Charlie and the Chocolate Factory as well in this case? What do you think?
Yes, so why would we do research if we thought that it would be impossible? Of course, but we have to adhere to all the stuff we have learned over the past decades in security, because we have come along, that the whole security community, not only in the OT and robotics world, has come a very long way and learned a lot of valuable lessons. And I think if you do it according to the procedures, to the standards that we have, if you continuously assess it and improve the security, I think you can do this. And there have been a lot of processes and measures proposed, like the DevSecOps cycle and so on, that can really help you go into a secure direction. But we also see that the complexity of the system also demands a lot of work in order to get this done.
Mina, what's your take on how far are we away from a full autonomous factory?
Well, from the production engineering point of view, we are very, very far from the fully automated factory. It is, in fact, my dream that there would be more automated factories. We don't have enough engineers to work in the future, so the birth rates are dropping, and people are not interested on the science and engineering. So we have lack of personnel. So I sort of hope that the robots would invade the factories. And from the safety perspective, those would be very safe for the human if the human is not there. From the security point of view, I think it's completely different then. And the access control might be quite an issue in the future. And yeah, it's going to be quite interesting, but the fully automated factories are still quite far from the SMEs.
What do you think?
I was going to say, I do think the trend to collaborative robots is going to cause some interesting areas that people aren't aware of, right? Once the, if the robots are all caged, yes, you can get in and hack and cause problems. But now if the robot's next to a human, and you can cause physical damage, or to hurt a person, I think that's a very different scenario. And so UR just announced that they had shipped their 50,000 robot. Now, compared to KUKA and Fennec and all those guys, that's a small number. But considering that they've only been around for a couple of years, collaborative robots have really been around for less than 10 years. That's a huge increase, and I think we're going to continue to see that. And those robots tend to just be more insecure, as I think Andika can talk about. And so the more widely they get deployed, the more this is going to be a concerning issue.
Especially when we move to the large-scale industrial robotics on the heavy-duty assembly, where they are actually needed, and we are still trying to remove the fences from those applications. And it is indeed quite a big challenge if the robot crushes the human, be it on the misuse of the robotics or by the hacking, but it will most likely disrupt the whole production on that factory site, and will lead to of course, the court cases. And of course, that will be challenging for that company, and the company will take quite much of losses on the monetary side as well as on the personal side.
If I may add, one of the topics that has already been mentioned, but I want to emphasize, is that once you have to reason about multi-agents, then the problems become more complex. So basically now you had to worry about not just hacking a single robot, but then hacking the dynamics of a factory, because you had to coordinate multiple agents. In the context of autonomous vehicles, perhaps it's even clearer that you don't have to, you had to go beyond just hacking a single vehicle, but then there are complex dynamics that happen with multiple vehicles basically sharing the space. And you can imagine that the types of concerns are not just physical objects that look like the perturbations that I mentioned or that I illustrated in the videos, but actually behavior from multiple vehicles that may affect the decision making of other vehicles, and then the dynamics can become fairly complex as we deal with the multi-agent problem.
So Anders, I was actually just going to point to you in that respect. Do you think that on the basis of some of the works that you've been doing, you see some opportunities also to enhance this security challenge that we are facing with the robots? Or in other words, can also the some of the research that you've been doing and some of the capabilities of detection and using AI be beneficiary to develop security products that can actually help? I mean, in the same way that you have been explaining about the driving.
Absolutely. So actually, I should have mentioned that some of the concepts that we're pursuing in the context of autonomous vehicles have also been applied to the context of PNT assurance. PNT is standing for positioning, navigation, and timing. And you can imagine there you have similar problems where you want to make inferences about position or time based on a variety of sensors. You know, you can deal with information from satellites, but you can deal with other real-time clocks and inertial measuring units. And then you had to reason about the extent to which many of these sensors can be manipulated and come up with the decision of kind of trust on the position that I'm getting out of this platform right now. And it will depend not just on the sensors that you have, but also on the various other situational awareness mechanisms that you have. And so some of the technique that we've applied to the context of autonomous vehicles have been also applied elsewhere. And we see potential for a fundamental approach that has some applicability to other domains, including many important for robotics.
Eric, what's your take on some of the ideas here? For instance, the applicability of more analytics into the robotic systems. How easy would it be to help us working on specific products and technologies that can assist in becoming more cyber secure also for the robots?
Yeah, I think, well, so the first point I thought, because it's very appropriate when you're talking about supply chains and robotics, because what you describe the current attack against the SolarWinds Orion system, that would be a supply chain attack. So you can just see the impact that has. And then you could ask yourself when it happens in a robotic supply chain. And that also brings the complexity, that just highlights the complexity of components and the weakest link in the chain. So that already sits there. And the basic point with security, come back with again, is attack surface size. So adding more analysis and more sensors, yes. What's the complexity increase, and can it be manipulated? Then another interesting point where you were talking about multi-agent system, which we want to be discovering more. I'm not sure. So if you heard of the Mirai botnet attack, so that was one of the larger botnets, and what that did was that it compromised IoT devices, and the first thing it did was to kick out other bots from those devices. It was great at doing cybersecurity because only that bot master wanted to control those devices. So what we're looking at for research is this. It's not that you have attackers and defenders. It's like you have multiplying conflicts within attackers and within defenders as well. So you think of your organization, because again, you come back and talk to your factories, you say like, I want it to be secure, but I also want it to be accessible. That's where always you talk about the stakeholders and everything. You're saying, how can you get the stakeholder to care about security, because they care about something else. So it's really the rise of complexity, and that strikes me. And then, since I haven't dealt with robotics that much, it's fascinating hearing all the extra robotics complexity that you're adding on. I find it very, very fascinating, and just again, like the swarm-like behaviors you could get from cars and everything like that. Yeah. I'm very excited. I'm not sure if I'm excited in a good and a bad way, but from a research point of view, man, it's interesting.
You're on mute, Ulrich.
Yeah, I see. So I think yes, and let's make that work. The other thing I was going to ask is it actually for the robots to in this case, for instance, learn from themselves or from their swarm, and in order to protect mechanisms to further defend themselves. I mean, in the same type of blue team, red team type of analysis that you showed. So how easy would it be for them to start learning also on the basis of the different environmental sensors that Anders was showing, that we can actually use the robots to train themselves in order to become more cybersecure?
So did you ask me? Sorry.
Yes. Sorry.
Oh, yeah. No. So I think I very much agree with what Andres was saying about using multiple sensors. Like in a way that's as we were looking at the mitigation, is the way of saying, like, if we can't trust a single source, maybe we need to use multiple sources to gain trust from. So that's why more sensors, and you'd hope from the probability of not having all of them compromised in a sense. So that decentralization is what you're hoping, and then other things, heterogeneous systems could be harder to compromise as well. But then again, you always have the weak links in the chain. So like security holds in a general sense, regardless in which domain you're sitting. Like robotics versus cybersecurity, you still have the same weak points, and you can still get the same benefits from other points. So it's very much about, needing to care about it from the beginning, triangulating your assurances and updating it all the time. Because again, another security point of view is the moving target defense. So maybe that, which is, because that's the other point where you say in security, you talk about zero-day exploits, which is you release something, there's an exploit when you release it and you don't know about it. So one way you think about it in security is say you need to have a moving target defense, because the only assumption you can do is that your adversary is already in your system. So then you need to adapt that security accordingly. So that seemed like, from a robotics point of view, that seemed like that's something you needed to take into account accordingly as well, is having some moving target type defense.
If I will, okay.
No, go please.
I will say that it is kind of a moving target already when you think of some of these mobile robots in warehouses and factories. They all build their own maps. Each vendor builds their own maps, and there is no coordination amongst the maps. And so if robot A builds a map, robot B has no idea where it is on that map. It can't correlate to that map. And so a hacker has to actually come in and essentially make changes to each of the robots independently, because they are not coordinated. And I will say right now, even vendors who supply multiple robots, we still see robot dance, what we call robot dances, but robots will be in an aisle, they'll turn around, they'll see another robot and they won't know what to do. And they'll kind of do this little bob and weave and dance. And it just slows the whole process down. They're not smart enough amongst themselves. We don't even have to hack them. They're already not intelligent enough to understand how to move around themselves. So still got a long way to go.
So going to the final couple of words here on for this event, and real it's getting close to just a couple of what's your expectation?
I think we're losing you, Ulrich.
And then, of course, also to some of the up and coming. one point.
Ulrich, I didn't hear the full
Delay
question.
on my side. Okay.
Yeah.
So question. Yeah.
Well, I'm gonna infer the question, and if I may, one of the points I would like to make is that defenses to the AI components of a system may not necessarily be in the AI algorithms themselves. It could be complementary. So, for example, in the case of using AI for network defense, and when you're actually trying to come up with strategies that can be learned to defend networks using honey networks and software-defined networks, you also had to guarantee that actions on network or configurations satisfy, for instance, traversal goals that you care about, right? And so you had to make sure that when the agent performs a particular network configuration, you don't inadvertently violate some of the security goals that you have in mind. And so that may come from a different type of research, for instance, in network security, and in fact, software-defined network research, that problem has been addressed to some extent, and it's important to take the learnings from that community as well.
Interesting. So just let me repeat my question just before. Sorry for the interruption. I'm back on the fixed network, which is a bit more reliable. So my question was actually looking towards closing this year with a couple of key questions. How we can look towards the next year, 2021, and what would you see, all of you, basically as major developments, major things that we need to watch out for, things that could impact us in many different ways, and then specifically, of course, here in the robotics field. And I was actually first asking to you, Mina, what sort of developments are you seeing that will happen, that are happening today, that will impact the whole robotics world in the next upcoming years, and that we should basically take into consideration also from the wider angle?
I would say that from my perspective, the digital value chain is one of the key topics. So that will put quite a lot of emphasis on these small companies joining to the larger network. And while the large companies, they have expertise for the cybersecurity, the supply chain doesn't have. And somehow, I think the cybersecurity should be raised as a sort of a topic even more. It's quite nicely getting a little bit the airtime on the European Commission side on the robotics and manufacturing field, which I'm following. But the digital value chain is now all about the technology and how we can integrate everything together so that the connectivity is the key. And that's something, well, there is the dark side, and we should address that as well. Also, I would like to see these case examples that what does it mean for a small SME, that what happens when they face the cybersecurity attack. It's not as in the agent movies, it's not Tom Cruise coming to steal your robot or program it in a fancy way, but what in reality happens and what are the implications to the production and to the actually the whole situation what the company has on the monetary wise. So that's would be the interesting topics.
Thanks for those, and I think also within Trinity, that's definitely something that we can start watching over to and looking into as part of the next year's program activities. Okay, thanks for that, Mina. What's your take on it, Tom? And I would say maybe also including some new developments such as robots on 5G, which are experimented with on many different places around the world. What do you see as the major things that we should be expecting in 2021?
Yeah, so you mentioned 5G, which is an interesting one. Just certainly, I think robots are going to continue to be deployed more widely with more connection methods. 5G is one. I think the one that I'm really interested in is to see what happens with ROS, and we talked about this a little bit yesterday. ROS 2.0, how widely is that going to be deployed? Are they addressing security more early on? We talked about, it's so difficult to squirt security in at the end. And then they're still competing. There's secure ROS or SROS versus ROS 2.0. Because a large portion of the industry is starting to use ROS, I think it's really interesting to see how the deployment of the next generation of ROS will happen, and how the security hooks that have been put in that will be implemented. So that's the big trend I think I'm looking for in 2021.
Yeah, and I think it's very much also in line with what Mino was saying, because I think ROS is really an opener towards the SMEs, allowing for existing tools and technologies and developments to be reutilized, existing experiences, and basically lowering the barrier to entry for many companies. So that I think is indeed a very in line. Then coming over to you, Eric, what do you reckon is going to be something that we would need to look out for when it comes to, for instance, AI world? I think there's a lot of expectation towards AI, probably over expectation. Is 2021 going to be the year that AI is going to fail?
No, I don't think so, because there's still plenty of progress that it come in. So I don't really see 2021 being the AI winter, the new AI winter. I more see, in a sense, though, the security being highlighted in a sense. That's the thing. Like with everyone spending more time remote working and people starting to wonder where's my data and who's looking after it and who's doing the selections. That's where I see. So I just basically see more security focus, and I think, as you were discussing beforehand, there's only so much security that can be in the headline. So the question is, which security is going to be highlighted first? And I think probably robot security won't be top in 2021, but it's going to come there. But so it's more going to be, again, remote working security and existing cybersecurity. But then it's going to slowly be shifting, but it's not next year. That's my. Thanks
for that, Andres. What are your plans for 2021? Are you going to continue on the same path, or specific other plans?
Indeed, this is a project that it's ongoing, and we have plans for FY21 to actually have a tool that we can share with the community, so that people who are developing decision-making platforms for autonomous vehicles start integrating security or defense mechanisms and reason about the extent to which they're effective against mitigating threats that we know about today. And hopefully that results in more secure and safer autonomous vehicles in the future. And we don't have to wait till we have full autonomy. There are already important autonomous features that are being deployed on vehicles today, and we need to have people looking at this problem even on current autonomy level features.
So just for all of you that you know, there's been a point raised by Jonas, who was speaking yesterday as well, actually. I think 5G is so complex, he writes, that nobody can verify its security for safety-related components. Hence, we'll look at 5G as a back channel for many years. So yeah, I'm not sure that I'm entirely agreeing there with you, Jonas, but that's of course my privilege now that I'm sitting on this side of the street and you're sitting on the attendee side. But I think there's actually quite a lot of transparency being created in 5G. Also, there's a lot of documentation in that respect, also from the European Commission. So from my end, I would say that a lot has been happened in terms of cybersecurity for 5G, that we can start to see how it's being improved. So I'm less worried in that space, at least from the 5G back channel. On the other hand, and there definitely you're right, there's still too many uncertainties about 5G. It's not yet full standard, and definitely not on the security side. But I think it opens up quite a lot of potential for security that otherwise would have been managed, like in the robot case with VPNs, that now can be managed in a completely different way. So, but thanks for pointing out and for raising it. Okay, so then last but not least, Bernard, what do you see coming up in 2021, and what's your big thing going to be?
Well, I would guess something that will very nicely combine this. We also heard that on the ROS Industrial Conference, and it's also in the IFR study. I think that service robotics will really take off. We already see it now, but it will be increasing more and more. Also outside of industry, so it's not going to be just intralogistics, but also areas like public spaces, agriculture, and whatever. And they will combine a lot of stuff that we have just mentioned in the last few minutes, because the whole AI developments that you will see in cars in the future, you will also try to utilize that already in service robotics in a smaller scale. 5G for connectivity will be an essential point wherever a robot needs to be connected. I think in especially in 5G, you will see more connectivity. So you will have robots even more connected without necessarily having so many layers in between, because the machine-to-machine communication that you will have, and we also using 5G as part of our local playground, where we are also having our robots connected via 5G. That will be a very interesting thing to see if this actually will make it easier for an attacker to get from one device to another. I think so. I can only agree with everyone before me that all of those trends will be increasing and more important in the coming years. I think also from the COVID crisis, we will have a lot of learnings, getting productions back to Europe, to the US, which will pose a lot of automation challenges that will have to be solved in time pressure, again, forgetting about security. However, on the positive side, I think we see a lot of developments in the right direction, be it the standards that are being developed, machinery directive, where I'm sure if robots in Europe have to adhere to security principles, just like we see it with the GDPR, this will go over the whole world. So I'm a little positive in some areas, but of course there is still a lot of stuff to do.
Okay, and then finally, can I congratulate you with your great shirt that you put on just for the purpose of the day? Yeah, you'll have to talk because people can't see it right now. So.
Okay, yes, I hope you can see it now. Yeah. Okay, now it seems to be working.
Perfect. Yeah, so I put my party hat on. As you can see, it's a virtual one, so I can't really put it off. But I already had my red-nosed reindeer sweater on for the whole day. So I think we're ready to start going into Christmas seasoning and settings now. We've taken the last 2 days really as a mechanism, I would say, for two major things. One is to really say, okay, we wanted to make sure that we were still capable of doing a CyberSecurity for Robotics conference in 2020. With the whole pandemic, it wasn't really feasible to do it still in a face-to-face fashion. So we've accomplished at least that we've done this, and I think it was definitely worthwhile because we've opened up new worlds. We've been able to log in from many different heterogeneous views, on what it's going to becoming like in the next couple of years. And at the same time, since many people couldn't go to any office parties or Christmas gatherings in any case, at least we have taken the time to be together and to at least talk about some of the topics that were really close to us and important to us. And so very happy to have received all of your inputs, ladies and gentlemen, and thanks for contributing quite lively. Thanks to my fellow co-organizers, Tom from Mass Robotics and his colleagues, Bernard from Joanneum Research and his colleagues, Endika and Victor from Elias Robotics. And of course, the whole of my team, including Mina from Trinity, from LSEC. So thanks a lot for participating and for viewing. And I'm sure that this is going to be yet another milestone for us going forward. And I'm looking forward to see you again, definitely all next year. Maybe partially still virtual, but at least also partial face-to-face. Thank you very much all. And I see that Jirki is sending P.S. Ulrich, my daughter thinks your sweater is quite nice. Well, thank you very much, Jirki. I think that too.
Well, Ulrich, thank you for organizing. Yes. I know it's tough to do these things virtually and pull it all together. You did a fantastic job. The great agenda and everything flowed well. Only minor little technical challenges, which given today, it's not bad. So thank you very much. Appreciate it.
Yes, thank you very much, everybody.
Thank you very much.
Thanks, Ulrich, for taking the lead. Kudos, and thanks very much for coordinating such a great event. Fantastic job. From the Basque Country, the warmest desires and Merry Christmas to everyone overseas, Europe, everywhere. So
thank you.
Really happy to follow up in the next CSfR events.
Absolutely, and wishing you all a great season's end. Merry Christmas, Happy New Year to both Europe and crossing the Atlantic. I think what we've really accomplished today, also thanks to the virtual, is making it a much more global community. So have a nice weekend and stay safe. Bye-bye.
Thank you.
Bye.
Stay safe. Stay secure.
Bye.
Bye.